an international recognized supplier of glass solutions which export its products to over 20 countries. The wine is in this, the Moldavian wine is in these bottles. And to Mr. Mihai Naki and Dr. Marco Sommariva from Malvern Analytical BV Company, a leading provider of scientific instrumentation for the measurement of elemental concentration, crystallographic structure, rheology, particle size, and so on. It is an opportune time to renew contacts and discuss problems of mutual interest with delegates from various institutions and countries. The agenda of the conference and the workshops cover a wide range of very challenging items related to condensed matter theory, design and structural characterization of materials, solid-state nanophysics, and for renewable energy. Roslav Moskalenko and Vsevolod Moskalenko, whose 90th anniversary will be tomorrow. To our deep sorrow, this year, academician Vsevolod Moskalenko has passed to a better world. Last year, the chairman of the program committee of all our previous conferences, academician Professor Valeriu Cancer, passed away. Please stand for a moment of silence to honor the memory of this scientist. Thank you. Thank you. But life should go on. And tomorrow we will say special happy birthday to Professor Sviatoslav Moskalenko, who will make a report a bit later today, and who invites you to a special coffee break at 4 o'clock tomorrow. Let me return to the work of the conference and workshops. I do hope you will share our visions of new research opportunities that, foreseeable on the horizon, will trace new direction of research. But, as English say, all work and no play make Jack a dull boy. So this is why the organizers have prepared also a couple of relaxation activities for you. Concert today evening, then excursion and trips to Moldovan countrysides. In concluding, I wish you every success in your presentations and discussions and a very pleasant stay in Moldova over these 4 days. And now it is my pleasure to give the floor to Professor Florentin Paladi for science or research of Moldova State University. This university is the host of our meetings during these days. Please.
Thank you very much. Dear colleagues, partners, and distinguished guests, welcome to Moldova State University. A few words about the university. I would like to say that Moldova State University is the biggest public university in the Republic of Moldova, with full range of curricula and research area. Almost all research area can be found out at the university. Today, the university comprises 12 faculties, about 1,200 teaching and research staff, including nearly 90 doctor habilitat and 400 PhDs, and about 12,000 students. The academic offer consists of 81 specialties at the bachelor level and more than 100 master programs, as well as 107 PhD programs developed at 11 doctoral schools. Of course, because we are at the research conference, I would like to say a few words about the research potential of our university. So, we think and we are proud that the research potential is the biggest in the country among the universities. There are 175 research staff units and almost 280 people working in more than 35 national and international research projects. We are, as a university, which have 21 research labs. Among them, there are 5 research labs in physics, and I would like to mention them. So there are labs in semiconductor physics, photothermoplastic registration, physics and engineering of nanomaterials and synergetics named after distinguished Professor Evgeny Pokatilov, photonics and physical metrology, organic and inorganic materials in optoelectronics, as well as we are proud to mention the Regional Interdisciplinary Scientific and Educational Center for the Study of Advanced Materials at the Moldova State University. We also are proud to mention that our 2 physics departments have a long-lasting history of more than 65 years. Last but not least, I would like to mention that the Moldova State University is top place among the all national universities in ranking of the universities. Finally, I would like to mention that the research and innovation at the Moldova State University are complex activities with important objectives of training students, development of their creativity, support and spread of international cooperation. On behalf of the University Management and personally the Rector, Professor Georgi Ciocanu, we wish you great and insightful discussion during the conference, fruitful project and success in research, now and in the future. Thank you very much.
Now I ask Dr. Elena Belei to say a few sweet words, I hope.
Doamnelor și domnilor, distinsă audiență, o să-mi permit să vorbesc în română din 2 sau chiar 3 considerente. Mă uit la fizică ca la o planetă foarte apropiată, dar suficient de îndepărtată și mi-e frică să nu greșesc. 2. Sunt în fața unui auditoriu foarte, foarte diferit decât cel pe care sunt obișnuită să-l văd în incinta acestei facultăți. Facultate care, de fapt, este casa unde eu lucrez.
Dear guests, distinguished participants, so I would like to speak in Romanian today, all 2 reasons. First of all, physics is a very challenging field, but it's not my field, and I see so many faces here. I wouldn't like to be just not on the level. And of course, physics is so attractive that sometimes I would like to join this physical area. But now I welcome you to my home faculty, the Faculty of Law.
Sunt și emoționată, spuneam, dar sunt deosebit de onorată să reprezint aici, nu Facultatea de Drept, ci Ministerul Educației, Culturii și Cercetării. Un minister care este mai nou preocupat de domeniul cercetării la nivel de politici naționale.
So, of course, Dr. Belei has some emotions speaking here. She is the graduate of this faculty. She worked here, but now she is representative, our state secretary, actually vice minister of the Ministry of Education, Culture and Research. Newly formed, quite recently formed section of the ministry that was separately Ministry of Culture, Ministry of Education. But now they are all together in one, and Dr. Belei is Secretary of State responsible for research.
Sinergia pe care Ministerul își propune să o promoveze între universități și institute de cercetare este un exemplu elocvent prin evenimentul de astăzi.
And the main objective of the ministry is to combine the research and research development of research universities and research institutes and universities of education. This conference is an eloquent example of that.
Salut și sunt mândră de Institutul de Fizică Aplicată și de Facultatea de Fizică și Inginerie a Universității de Stat, care și-au consolidat eforturile și au reușit să pună în evidență o tradiție. Înțeleg că această conferință este undeva la 6-a, 7-a ediție. A noua, scuzați-mă, așa mai stau acolo.
Well, Dr. is happy to see this fusion of the Institute of Applied Physics and the Faculty of Physics and Engineering of Moldova State University, the fusion that has been lasting for quite many years, because this is already the 9th edition of the conference.
O altă finalitate pe care sunt deosebit de mândră să o constat în acest auditoriu cu ocazia acestui eveniment este internaționalizarea cercetării. Cercetarea nu are limite și nu are coloratură politică.
So there is one more very important moment that Dr. Day would like to mention. This is the international range of research which is demonstrated by the participants of this conference. In research, in science, there are no borders, no political activities, just research and science.
Tocmai mă gândeam să constat cu o ușoară doză de amărăciune lipsa tinerilor în auditoriu când au intrat tineri puțini, dar buni, sper, ca fiind participanți la această conferință.
Well, that's a pity that Dr. Blair didn't notice very many younger researchers participating here, but most probably this is a problem of transportation, not of physical education.
Sper că oaspeții care poate nu sunt pentru prima dată în Republica Moldova au descoperit nu doar o fizică din Moldova, cercetarea în domeniul fizicii, dar și o altă Moldovă, tocmai este timpul vinificației și a sărbătorilor.
Well, Dr. Blake hopes that the people who are here will enjoy not only the new visions and results of our physicists, but also will enjoy the results of the work of our wine makers. This is the top of their season.
Și un ultim motiv, dar nu cel din urmă, de a fi prezent aici cu deosebite emoții, este să cunosc o legendă vie. Domnul Sviatoslav, care astăzi mi-a oferit ocazia să-l ating. Știu că fizicienii nu sunt superstițioși, dacă o să permit să vă felicit anticipat cu o frumoasă aniversare din numele doamnei ministru Monica Babuc. Nu o să vă supărați pe noi.
So it's a very special occasion, a special pleasure for Dr. Blay to meet here our jubilant academician Moskalenko, who will be 90 tomorrow. And Dr. Blay is honored and happy to transmit to his family, to him, the best wishes on behalf of the Minister of Education, Culture and Research, Ms. Monica Babuc.
Florile de toamnă sunt foarte rezistente și este o aluzie foarte transparentă la faptul că foarte mulți din cei prezenți în sală și-ar dori să atingă culmile pe care dumneavoastră ne le-ați descoperit și ne-ați arătat.
Well, you can see autumn flowers here that are so resistant to any rains and rains and sun, and Governor Belay hopes that we all will follow the example of the resistance in science and life of academician Moskalenko.
Florile sunt foarte puține de
So that's a very modest sign of our appreciation, says Dr. Belay.
Participanților le doresc o ședere plăcută și o conferință foarte interesantă.
And to wind up, Dr. Belay wishes all the participants fruitful discussions and interesting time in our city. Thank you.
Thank you. And now I ask Dr. Popovici to say a few words. That's thank you.
Doamnelor și domnilor, onorată asistență, permiteți-mi în numele șefului statului Republicii Președintelui Republicii Moldova, domnului Igor Dodon, să vă salut la acest prestigios for internațional, să vă doresc succese, noi idei, discuții constructive pentru dezvoltarea științei din țara noastră și nu numai. Consider că acest important for științific încă o dată denotă prestigiul și valoarea pe care o prezintă școala fizico-tehnică din Republica Moldova.
Dear guests, honored participants to the conference of this prestigious international event, the representative of the Presidency of the Republic of Moldova, Mr. Popovich, would like to transmit to you on behalf of the President of the Republic of Moldova successes and just wonderful results in your discussions and in your further research in physics and technology.
Sunt sigur că forul de astăzi va contribui și la sensibilizarea opiniei publice din țara noastră, dar și din străinătate, la unele probleme care sunt în știința din Republica Moldova.
Mr. Popovich expresses his hope that discussions of today and the following days will not only bring the scientific results, but will also contribute to the popularization of science and research, of Moldovan and other countries' research among different population strata.
La etapa actuală, țara noastră se ciocnește cu un șir de probleme, cum ar fi micșorarea considerabilă a numărului tinerilor care vin în știință.
Well, unfortunately, one of the major problems of our country is a very low income of young researchers in science.
La etapa actuală sunt și un șir de modificări la cadrul normativ care, în viziunea președinției, nu sunt benefice dezvoltării științei din Republica Moldova.
Well, this is the vision of the presidency of the Republic of Moldova, that some of the transformations and reforms that has already started were not to the benefit of research and science.
În special, diminuarea importanței Academiei de Științe din țara noastră și a institutelor din cadrul Academiei de Științe.
First of all, Mr. Popovich is speaking about the reform in the Academy of Sciences and the destiny of the academical scientific institutions.
Sunt convins că împreună cu comunitatea academică, cu comunitatea științifică din țara noastră,
Well, Mr. Popovich expresses his profound hope that together with the scientific community of our country,
noi vom reuși să deschidem noi perspective pentru dezvoltarea științei moldovenești.
not only the perspectives for the development of Moldovan science will be further developed,
Iar forul de astăzi va reprezenta un factor important în ceea ce privește promovarea imaginii țării noastre în străinătate.
well, Mr. Popovich expresses his absolute conviction that this international forum today, this international conference, will promote the image of Moldova all over the world.
Pare partenerilor străini.
Well, another hope is that this forum, the conference and the workshops will contribute to attracting investments in research and science and will help in the further development of this scientific orientation of our country.
Deoarece noi suntem convinși la președinție că saltul Moldovei este posibil doar prin inovare, doar prin știință, doar prin cultură.
The representatives of the presidency are absolutely convinced that a jump up of Moldova is only through innovations, developments and culture.
Vă doresc succese, discuții constructive și cei care sunt pentru prima dată în Moldova, vă mai așteptăm. Avem o țară frumoasă și oameni foarte pricepuți.
Well, at the end, Mr. Popovich wishes all successes to participants in the conference, and those who are here for the first time will certainly come again visiting this wonderful city, this wonderful country, because the people are the asset of this country.
And now it's my pleasure to give the floor to our colleague, physicist, a great specialist in nanophysics, nanotechnology, first vice president of the Academy.
Thank you.
As you like.
Dear chairs of the conference and members of the presidium, dear guests, dear colleagues, good morning. First of all, on behalf of the presidium of the Academy of Sciences of Moldova, I would like to congratulate you with the opening of the 9th International Conference on Materials Science and Condensed Matter Physics. I remember the year of 1990, September. It means 28 years ago. Practically the first real international conference was organized here in Chisinau. Happy that after 20 years, after nearly 30 years, this tradition that was initiated at that time by academician Sergio Rădăuțan continues successfully, and the International Conference on Material Science and Condensed Matter Physics, it's already a good tradition each 2 years to meet together to discuss scientific issues of mutual interest, which is very important for us in the Republic of Moldova, because due to the lack of funds, we apply to European funding institutions, including the Horizon 2020. And of course, to be successful, one needs to create consortia with strong partners from other European countries. And this is a very good possibility for us, for all guests, to discuss new ideas, to initiate new projects. I came a few days ago from Brussels. I can tell you that there will be new programs launched in the near future, and of course the success will depend upon the scientific excellence of projects that will be submitted, and therefore I wish you to successfully use the time and to discuss and initiate new projects. This conference is also important from another point of view. We celebrate 90 years of the so-called Moskalenka phenomenon. Two brothers they made history of science, and not only in the Republic of Moldova, but at the international level. Frații Moskalenko au făcut istorie științei, și nu numai în Republica Moldova, dar la scară internațională. Spun lucrul acesta fiindcă am avut posibilitate să prezint referate în multe țări ale lumii. Și dacă venea vorba de fenomene care au fost studiate de frații Moskalenko, vreau să menționez că întotdeauna spuneau, da, am auzit, da, îi cunosc, sunt poate dintre cei mai cunoscuți savanți ai Republicii Moldova peste hotarele țării. And I would like to note that academician Vsevolod Moskalenko, who proposed the theory, developed the theory of two band superconductivity. Academician Sviatoslav Moskalenko, who discovered, let's say, theoretically, but for the first time published a paper on biexcitons and actually proposed theoretically the Bose-Einstein condensation of excitons. And later, all these theoretical predictions have been proved experimentally. Și vreau să menționez că academicianul Sviatoslav Moskalenko, mâine o să-l felicităm cu aniversarea 90-a, este primul și unicul laureat al premiului de stat al Uniunii Sovietice din Republica Moldova în domeniul științei. Frații Moskalenko au făcut istorie și, domnule academician, noi vă mulțumim dumneavoastră pentru dăruire, pentru consacrare. Știm că viața dumneavoastră a însemnat și înseamnă cercetarea științifică. Și sunteți un exemplu, un bun exemplu pentru toate generațiile mai tinere. În context vreau să aduc mulțumiri și cercetătorilor care au depus eforturi ca să creeze acea broșură, acea carte despre frații academicieni Moskalenko și, în primul rând, domnului academician Mircea Bologa, domnul doctor Igor Podlesny, și domnul doctor Leonid Dogotari, și desigur că a contribuit și academicianul Sviatoslav Moskalenko și o să revin la dumnealui.
Domnul director al Institutului de Fizică Aplicată, doctor habilitat Mihai Macovei.
Și domnul doctor Mihai Macovei, cu plăcere menționez, deoarece eu am luat ceea ce e scris în carte. Dar desigur că directorul contribuie permanent la toate inițiativele. Cu o deosebită plăcere vreau să și am onoarea să înmânez domnului academician Sviatoslav Moskalenko medalia Meritul științific de gradul 1 conform deciziei Prezidiului Academiei de Științe a Moldovei. Medalia Meritul științific gradul 1 se conferă domnului Sviatoslav Moskalenko, membru titular al Academiei de Științe a Moldovei, pentru realizări de rezonanță în cercetarea științifică fundamentală și aplicativă și în legătură cu aniversarea a 90 de ani, semnat academicianul Gheorghe Duca, președintele Academiei de Științe a Moldovei. Cu părere de rău, dumnealui nu are posibilitate să fie în această dimineață împreună cu noi. Domnul academician, vin la dumneavoastră eu. Eu vin eu. În primul rând, eu vă felicit. Aveți multă sănătate și plan să-l păstrați încă mulți ani. Vreau să vă spun că dacă ne întreb
Eu sunt mai mult la distanță lungă.
La distanță lungă. Cu atâta dreptate și noi realizăm.
La distanță.
I would like to know that academician Moskalenko submitted recently a project to the European Training Program. I mean, he is active, is doing science at a higher level, and actually it's a pleasure to work with him. Sănătate și succes, domnul academician. Asta e dumneavoastră. Asta e...
Emission was awarded and decorated with a medal for scientific contributions signed by the President of the Academy of Sciences of Moldova, Emission, present here. This is the medal and the diploma confirming his special contribution to the development of Moldovan and world physics.
Domnul academician, sănătate.
I should like to say some my gratitude to all of you for the offer to my brother Cellular Anatolyevich Moskalenko and to me. It's a great collaborators taking making effort to make all the best and all which is in our capacity and ability. We are honored today. It's a great pity that my brother is not present here. He is leader between both of us. He is a noble and devoted man, scientific collaborator for the science. All his life was playing with maximal efforts to do and to penetrate and complicated questions related with strong correlated electron systems, to elaborate even such new methods of description which are not known, which are not based on the Sedation theory. It's very complicated questions to which were applied the effort of more eminent physical theoretical physicists in the world. It is a great success for him to elaborate the theory of the superconductivity, generalizing that theory by Barden, Cooper, and Schrieffer in the case of many bands superconductors. It was a question which arrived immediately after the elaboration by Barden, Cooper, and Schrieffer of their famous theory of superconductivity in 1957. Just this performance of the theoretical physics of the universal meaning, this achievement in the theoretical physics and physics in general of the last century played and influenced enormously on all the physics, especially in condensed matter physics. And it influenced as a supernova which influenced on the many galaxies In the same way, the theory of Barden-Cooper-Schrieffer and the theory elaborated and performed by Bogolubov immediately after the Barden-Cooper-Schrieffer achievement, this influence, these tentatives to elaborate, to generalize, to find new continuation and new possibility in the physics were used by many persons, including academician Cellular Moskalenko, and I, with great admiration, remember about his achievements, about his efforts, about his noblesse, about his devotement for the science. Thank you very much for your respect for his memory. Thank you very much also for the attention to my modest person, my modest approach. It was the approach which we are able and we are obliged to make being collaborated in the Institute of Applied Physics. The Institute of Applied Physics is the Admiral Institute of the Physics in Republic of Moldova. He has a great, important scientific privilege, traditions, and we must continue. We are obliged to make all possible to develop, to continue, and to realize the most important and favorable for our republic, for our society, for our people, to make all possible to continue and to be
Достойный.
to continue and to do all the best. Thank you very much for your attention.
Dear colleagues, do not forget that tomorrow at 4 o'clock, the birthday is tomorrow, is not today. So tomorrow at 4 o'clock we have the possibility to say something to Professor Academician Moskalenko. And now I would like to ask our director, Professor Mokovey, to say a few words about the Institute.
Da, nu cred că sunt locuri aici.
Nu cred, lăsați, stăm aici mai bine.
Trebuie de rezervat atunci când dai în față. A fost rezervat. Da. Și cum nu mai eu am trecut în toți, că oamenii care au învățat.
You can start.
Dear distinguished guests,
Take the microphone, please.
so dear distinguished guests, dear friends, first of all, I would like to express our gratitude to Professor Kuluk and his team from Institute of Applied Physics and Moldova State University for being able to organize this event already for many years in our condition. And in the next few slides, I will show you a little bit the Institute of Applied Physics and our famous people, Bravo Moskalenko. So the Institute of Applied Physics was founded in 1964, and the first director was the academician Lazarenko, who got the Soviet Union State Prize for in developing of electrical discharge machine. So then, at the moment, the Institute of Applied Physics consists from 10 research labs with around 160 researchers, and also we have auxiliary staff around 213 positions. Among these people, we have people with habilitations, doctors, academicians, and young scientists. The main research area of the Institute is the physics of condensed matter, semiconductor materials, including nanomaterials, quantum optics, optoelectronics, and also how to use electric fields to intensify heat and mass transfer or modification of material surfaces via electrophysical and electrochemical methods. We are always open for international collaboration, and on the next slide you will see our international projects. Because previously we get funding via Academy of Sciences of Moldova, then we have bilateral projects with Academy and the National Research Council of Italy, with Romania, Ukraine, Russia, and the Science and Technology Center in Ukraine funding comes from European Union and the US. NASA, we are proud to say that we have 3 H2020 Horizon 2020 projects and 1 project NATO. So on the next slide, I will show our famous people who are staying on the basis of this institution, I mean brothers Moskalenko. So if you look at this picture, I think it will be hard to distinguish these brother lives. Sometimes their girlfriends are mixing up there. So maybe tomorrow Akademician Moskalenko will tell us some funny story about this. So let's start with Akademician Sviatoslav Moskalenko, who was among the first to say, or discover this biexciton, which is like a bound state of 2 excitations. And he published more than 400 papers, and he has more than 20 PhD theses supervised. And also his working course is Bose-Einstein condensation of excitons and biexciton, and for this, his contribution in this field, in 1988, he got the Soviet Union state prize for this works. And then the next slide, let's turn to already academician Cellular Moskalenko, who unfortunately passed away this year. He's well known for his theoretical models of superconducting of these 2 bands and multi-bands, and especially in saying that due to this overlapping of these bands and strong correlations between the electrons, so that this temperature can be increased, and these models were experimentally demonstrated, and he is well known in this field. So actually he was quite famous and working with famous people. This is academician Bogolyubov, who was also his supervisor at both times. And I would like to, he also is known as being the official representative of the Republic of Moldova at the Joint Institute for Nuclear Research in Russia, and also he successfully supervised more than 20 PhD students and has more than 400 people. So with this final slide, I would like to say that brothers Moskalenko have indeed played an impeccable role in the development of theoretical physics in Moldova. Thank you for your attention, and hope to have a nice time.
Thank you. Good. And now I invite you to start our plenary session, and the first is Academician Moskalenko. It's your report. Yes? Yeah. And you go next. I will come back.
the beginning, I should like to thank the organizing committee for the great honor offered to me to take the report here in your presence. My report is related with the properties of the two-dimensional magnetoexcitons. I will talk about some words about the magnetoexcitons two-dimensional, after that about the molecule formation, about the Bose condensation, and some new trends which are related with the Chern-Simons field, related with the two-dimensional quantum point vortices. Here is presented the magnetoexcitons in difference on the Wannier mode exciton, which are similar with the hydrogen atom. Here, due the presence, due the action of the strong magnetic field, which is perpendicular to the layer, due this fact, because the Lorentz force depends not only on the magnetic field strength, but also on the velocity of the particles, due this fact, being strong, being much greater with the cyclotron frequencies greater than the binding energy in the Wannier mode exciton, due this fact, the magnetic field leads to quantization separately of electron and hole, and this distances between them depends on the wave vectors. By this reason, the magnetoexciton, which now is formed due to the Coulomb attraction between the electron and hole, nevertheless, in spite of the fact that it is secondary important force in comparison with the magnetic field, but it leads at the final stage to the formation of the magnetoexciton. But because the deviation and the gyration points depend on the velocity, on the wave vectors, due to this fact, the wave vector of the center of mass dictates and determines the distance between two clouds, two fields here formed by the electron density. Here is the electron and hole. They have the distance between them which is proportional to the wave vector. It means that the wave vector dictates also the Coulomb interaction. Between the Coulomb interaction it depends on the distance. In such a way, the Coulomb interaction determines the dispersion law, the dependence on wave vector. It is a strong interdependence. Another important property is the fact that the orbit of the Landau quantization for electron and hole do not depend on their effective masses. It depends only on the magnetic length. It's a very important property, and as a result, when the wave vector equals to zero, in this case the arm of the dipole moment is also zero. These two orbits are overposed, being the same radius. Be different charges, we obtain a completely neutral formation, and this neutral formation, with k vector two such magnetoexcitons with k vector 0, 1 and another, they do not interact. In such a way, we have deal with the ideal was a gas. This fact was for the first time understood by Lerner and Lozovic. In such a way, we have two important properties. This second property is about I talk, the equal radii which do not depend on the effective mass. This properties is known as hidden symmetry, and it will influence the following. Then Yes. When two magnetoexcitons are forming a molecule, in this case they are moving on the space in a confined space. As in this case, the distance and the position in the real space and in the wave vector are interconnected by the Heisenberg uncertainty relation, and by this fact we have here the wave vectors and the arm of the dipoles which are moving continuously in dependence on their motion. We can have great distance with small arms. We have possibility to have small distances with great arms. And due to this fact, we cannot describe them as two dipoles with rigid arms. As a result, we have introduced the wave vector, the wave function of their relative motion in the molecule frame, and this relative motion was described by the wave factors. It is possible momentum or a real space representation. In momentum representation, we choose such wave function which has the minimum as the point zero, because magnetoexciton K0 do not interact. They interact if they have only different wave vectors. In such a way, the most favorable for the binding wave function is the wave function with the maximum on the ring. Another properties which was taken into account is the spin structure. We have here 4 particles, not 2 as in hydrogen molecule case where the 2 protons were fixed and the quantum properties were not taken into account. We have the 2 electrons with opposite different spins. We have 2 holes with different spins. We have chosen some states, such of one of them electron, 2 electrons have correlated spin, singlet or triplet. 2 holes have singlet or triplet orientations. And now we can combine and we can construct the wave function with singlet pair electrons, singlet hole pairs, or triplet. Mixed states are forbidden to the hidden symmetry. As a result, we have now to do, I should like to add that we considered for spin structure, not only this singlet, triplet, but also para and ortho, when the spin of electron in the frame of each separated electron are oriented. In such a way, we have 4 spin structures. Not only singlet, triplet, but also para and para, ortho and ortho. Mixed also are forbidden. The main interaction which remain here after the action of the magnetic fields will dictate this initial situation when the electron and hole are on the lowest Landau levels, and the magnetoexciton is formed with wave vector and with arm. Now there remain only Coulomb interaction, which was taken into account directly, considering the interaction of the charges, but not of the dipoles, because the dipoles are changing continuously. After that, please, the next slide. Here, the Feynman diagrams which were taken into account, the Coulomb interaction. Here is presented Coulomb interaction. Please, no. Behind. Once again, here. We have the lines, black, continuous solid lines describe the electron, lines and dash describe the hole lines. There are lines with intersection, diagrams with intersection, without, and all this, please, next slide, all this diagram can be combined in two terms. It is interesting that for these four structures, spin structure, it is possible to have a single expression which needs some parameter eta, which describes the spin structure, and it takes four values, not only 1 minus 1, but 1/2 minus 1 minus 1. Please, next section, and here was obtained that the Coulomb interaction have for different parameter of the alpha is a variational parameter of the wave function, and for any parameters, the energy is or positive or greater than the energy of two free magnetic excitons. It means that all these states are unstable. All these bound states, the stable bound state, in this condition, in this approximation of the lowest Landau layers, in the presence of the hidden symmetry, such bound states do not exist. It's similar with some earlier obtained result by Puchkov and Rajba, but in spite of this, appear some new unknown dependence of the alpha. There exists one unbound bound state. This state is being, in fact, unstable, but it is metastable. It has a great activation barrier, and this great activation barrier gives sufficiently long lifetime and gives the possibility to obtain the new luminescence line. Please, next slide. It is here, it is shown that the dipole-dipole interaction cannot explain this situation, but it leads to one important result, that two dipole moments, not previous, please, two dipole moments with parallel dipole moments. Excuse me, that I think that they attract, but dipole moments with anti-parallel dipole repel. And it is not strange that we have not obtained the bound state, but in spite of this, the metastable bound state appear. This new state, please next slide, has the tunnelic properties. The tunnelic properties of this barrier were determined. It has a transparency of about 4%. It leads to the possibility to some hypothetical particles with this trapped, with this confined at the back of the barrier. These particles can tunnel, can escape, can evade from this bonds, metastable bound state in the time of a few picoseconds. In such a way, this state is sufficiently long time to obtain the next some physical consequences. Next slide, please. It is the possibility to search, to investigate the radiative recombination of the metastable bound state. The recombination takes place when the cavity photon appears if the system is embedded in the cavity. Then another magnetoexciton, which was the components of the bound state, it remains in the form of paramagnetoexciton. Because this paramagnetoexciton has the linear dispersion law, I will talk about that. In this case, the probability to obtain, to recombine, to have this recombination, it's about 10 in degree 10, 10 in degree 8. It depends on the band-to-band matrix elements. Please next, another properties is that this, because the energy, the minimal energy of the bound state is positive, not negative, because we have not binding, but we have metastable state. Due to this fact, the new luminescence band is situated at the greater energy side as regards the exciton luminescence line is contrary to the situation known in the case of Vanya mode exciton band. This line is named as M line of the exciton conversion is from the lower energy side. Please next slide. Because the para-exciton happen to have linear dispersion. This linear dispersion was unknown up till now. It appeared due to the fact that it was necessary to take into account the electron-hole exchange interaction. It's the case when the electron before and hole before the scattering and after the scattering are changed by their places, electron is transformed and hole and electron. This interaction being for the first sight being non-important, but in reality give rise to linear dispersion. This linear dispersion is completely different from the quadratic parabolic dispersion law, which was known up till now with the magnetic mass. This group velocity is proportional 1 plus C is 1 for para and minus 1 for water. In such a way, these properties is only proper for the paramagnetic excitons. And it is proportional to the oscillator strength of the excitons. Only the bright and the dipole active magnetic exciton has such a properties. And another properties is that this group velocity is increasing with the increasing of the magnetic field. The existence of such dispersion law is important because it leads to the Bose-Einstein condensation of the two-dimensional Bose gas at temperature different from zero, because it is known due to the theorem of Buchenberger that the Bose gas with quadratic dispersion law, with infinite surface of his situation, such dipole, such Bose gas can condense only at temperature equal to zero. And it is very interesting and very marvelous situation that the experimental physicists succeeded in spite of that to observe Bose condensation of two-dimensional exciton polaritons in the cavity at temperature different from zero. It happened because they succeeded to concentrate these polaritons on the confined, on the limited spot, light spot formed by the laser beam. But now we have the possibility to, we open the possibility to discuss in more simple and more accessible condition of the Bose condensation. It is important because now, if we can hope that the magnetic excitons with K vector different from zero, with great wave vectors, now can be considered, can be studied as a possible condensation. But they, as I demonstrated earlier, they have the attractive interaction. Being parallel in condensation, we have parallel wave vectors and parallel dipole moments. But in spite of that, we have the possibility, the chemical potential, this independence of physics factors, have a metastable state. In such a way, we have the possibility to obtain the metastable states, not only for the molecule formation, but also for the Bose condensation. But this Bose condensation is possible only in the condition when the filling factor is not greater, for example, by 1 divided by 3. Then, but now we must, because we arrived to such great concentration of the magnetoexcitons, then the filling factors for electron and hole on their Landau levels are fractional. In this case, we can answer to the question, what will happen with these magnetoexcitons when we met with the condition of fractional quantum Hall effect situation. Quantum Hall effect situation, as is well known, discovered, stunning, exceptional, no new state of the matter. This state of the matter was discovered in the case of one component, electron gas, two-dimensional and magnetic field on the surface. But now we have dealt with two-component electron-hole system. And the question is, what happened now with these new states which will be now appear? Because now we have the conditions possible to realize them. It is, please, next slide. It is known that, as was published in the many review papers, it is known that the new states and the new phenomena which appear as the conditions of fractional quantum Hall effect is the fact that the magnetic flux through the surface is quantized. It consists from quanta of flux, and this flux quanta have a number, have a value, and which is dependent by the surface and by the is a number of small surfaces with the radius equal to the magnetic length. This each in such a way we have n flux quanta which determined only by the surface. If the number of electrons is 3 or 2 times smaller than this number of n, in this case we have filling factor 1 divided by 3 or 1 divided by 2, and the phenomenon there that each flux quanta excited two-dimensional vortex, quantum vortex, and this vortex, there are n vortices, or it is possible to say about n fluxes, quanta. Verchik supposed that this each electron attached, if the number of electrons is smaller by 3 times, in this case for each electron attaches 3 flux quanta. Red reformulated this affirmation and proposed to consider that each electron attached 3 quantum point vortices. These quantum point vortices are in fact point-like. It means that their vorticity is only in the point 0 around which take place the rotation. Please, next slide. And here we now try to generalize this marvelous situation to understand what will happen with the electron hole system. In this case, this possibility, as was shown by Leary, it was possible to introduce mathematically by the field, by the unitary transformation proposed by Chern and Simons, and this now, our generalization consists in the fact that this phase operator, which is better to understand looking at its gradient. This gradient is nothing more than the vector potential. Appear new vector potential side by side with the external vector potential. This vector potential in our two-component electron flow system depends on the difference between the density of electrons and quarks. It is completely different situation with the one component electron gas, because in one component it was only 1/10. And in the mean field approximation, we can see that in our case, we will have in zero approximation, we must consider that this new vector potential is in a mean field approximation equal to 0 in such a way, in our case, in spite of the quantum point vortices which appear here as a result of such transformation, it is a mathematical possibility. But in our case, the mean field vector potential is 0. It means that the external magnetic field remains. It means that the Landau quantization remains. In such a way, but in spite of the new combined electron and holes now obey to the Fermi-Opposite statistics. And please next slide, I will. Here it is, but it is possible now to take into account the vector potential supplementary, which appear here is vector potential by the external and by the Chern-Simons field, and taking it into account as the first order perturbation, we can arrive to the conclusion that the effective mass, which there was only isotropic magnetic mass, now appear anisotropic magnetic mass, which depends, but it depends on the difference of masses and do not depend on the magnetic field strength. Thank you for the attention.
Question, please. Who has? Yeah, Professor Fomin.
Thank you very much for your very transparent and motivating work. I have one question concerning the consequences of Dirac cone in the energy spectrum. You consider the consequences in the sense of creation of localized topological effects, vortices. But if the sample is confined, if it is restricted, there can be also some topological state which occurs on the boundary of the system. And many efforts in modern physics of topological materials, as you know, are related to this edge effect. My question is whether in your system, due to the presence of this Dirac cone, which is just now shown on the screen, there might develop some edge state if the whole system is confined, if it is restricted in size, and can you consider something next to the quartz?
Interaction between the particles. Coulomb interaction was considered in our case in the homogeneous state, but not in the state which you are proposed. I think that if we can introduce the wave function of this electrons and holes, or all electrons, which belong not only to which are subjected not only to the Landau quantization without this.
It may be with.
In this case, we we must introduce a wave function which is slowly varying amplitude
In space.
having such symmetry. And it will appear the competition between the velocity but I must possible it is not so complicated because in our case the group velocity was symmetric, not asymmetric, and but it was possible it will be necessary to have group velocity on the radio of the torque. Possible. It's possible this will be the exit from this concordance, this opposite symmetries possible. I cannot, but it is very interesting question. I must think about this.
Thank you very much.
More questions? Yes, please. Oh, Ale.
A group of professors of Moscow just recently, 2 days ago, sent their deep regrets in connection with the die of your pupil and this young, which is younger as you, the Professor Haji, which participated in 1985 to a school of young scientists which took place here in Chisinau and Vadovi Water. And they knew them, they knew Professor Haji, and they regrets deeply his death. Second, also they...
Dr. Gain, it's not a question. You can say this tomorrow at 4 o'clock.
Okay. This article is from the Library of Missouri. Is an article by John Archibald Wheeler for Electrons, which was published in 1946, and which contains some predictions of existence of excitrons. I have received this article 2 days ago. This is a gift for you from the United States.
I should like to take the occasion and to remember Professor Haji because he is the author of our papers, and I should like to affirm, to say you, to inform you that this paper was possible to effectuate only due to participation of Professor Haji, who are a very known specialist not only in the theoretical physics, but only on the mathematical of the special functions. All our calculations very exact, and it was possible only using great efforts of all of us under the guidance of Professor Haji to make these calculations. Thank you.
Thank you. So, good. Next report is Professor Evers, X-ray quantum optics with nuclei. Yeah? For you. And this one as well.
Thank you very much. I first would like to say that I'm very happy for the invitation and the opportunity to speak here. And for me, it's the first visit to this country. And yesterday was already very exciting, and I'm looking forward for the next days. And thank you all already now. So, you may wonder what I'm doing at this conference with this title, but I hope to be able to convince you that there is actually a strong connection to material science related to this, even though our view is somewhat different. Maybe it's a more future perspective, but you will see. And right from the start, I show you also two pictures. This is actually the institute where we do our theory, and this is the European Syncope radiation facility in France, where we do the experiments, or we did the experiments that I'm also going to report today. And it's a nice combination of theory and experimental work. Let's start very simple. And I would like to remind you of the electromagnetic spectrum, which I really admire, because it means that people found a way to sort of unify these very diverse concepts in a simple theoretical framework. And if you look at the scales involved there, it's of course clear that light is the primary tool. Probably all of you are somewhat related to light. And in particular, the idea of combining different wavelengths is very favorable. The simple example would be my hand. If I show it to you, it maybe looks like this. Oops, I'm sorry. Looks like this. If you repeat the experiment with long wavelength radio waves, you would probably see nothing. And if you give it to the doctor you trust, this person can take a picture like this. And it's clear that the combination of all of these pictures gives you much more insight into the system you study. And that's of course used everywhere. Here's an example I like. It's actually 3 times the same part of the space in the galactic plane, only in different frequency ranges. And if you don't know that it's actually the same objects you see there, I think you would not be able to tell. And the combination, again, tells you a lot about the system. So now then, when you think about X-rays, the typical arguments in favor of X-rays, the typical things that come to mind are, of course, related to the small wavelength. If you come to this tool argument, that if you have, the small wavelength, then of course you can structure small, things, and you can also observe small things. And typical examples would be, of course, the structure of DNA that was discovered using these X-ray sources. And another thing which would be maybe more applied is, of course, this plan of microchip companies who want to use smaller and smaller wavelengths in order to structure smaller components in the computer to make them more powerful. However, my take at this is somewhat different, because I would be concerned with coherent control, resonance scattering, and so on. And so I would like to discuss what resonant interactions you can have with X-rays and materials. And as a concrete example, I take this iron, because this is the isotope we do our experiments with. And if you first of all look at the interaction of the X-rays with the electron shell, then you have a reference booklet which tells you that at a few kiloelectron volt, 7 kiloelectron volt, you can excite the lowest electrons to the continuum, maybe ionize the system. And what is interesting now for the rest of the talk is that the line width of these resonances is on the electron volt level, which means that the dynamic takes place on a femtosecond or less scale, so extremely fast. However, if you tune your X-ray source to slightly higher energies, around 14 kiloelectron volt, in this species you find actually an ultra-narrow resonance. And the interesting thing is that this you actually have to find in this data sheet. It's a nuclear data sheet, because it's actually a nuclear resonance. So what you do is you take the nucleus and excite it, and if you compare the numbers, this resonance is 9 orders of magnitude smaller in width in the spectrum than the electronic one. And this is actually the origin of a lot of applications also related to material science. So why is this? It's actually related to a lot of phenomena studied now, which are called the zero phonon transitions. So it turns out that in some materials, if you absorb X-rays or you emit them, it's possible to do this without the excitation of a phonon, because the entire crystal lattice takes up the momentum. And then you end up, if you have this, keep pushing the wrong button, if you have this energy or the recoil as a spectrum, you have a very narrow line with zero phonon peak, which is very narrow in the spectrum, and this is the origin of this nice feature of having a nuclear resonance which is so narrow. Now, immediately after the discovery by Mössbauer in '61, a lot of applications were found, and they are quite easy to understand, because what happens is that if you take this material and take these nuclei and put them in a substance, a compound or a chemical substance, you see modifications in the spectrum. So the resonance line can be shifted, for example, chemical shifts, you can have splittings, electric or magnetic. And if you then do spectroscopy on the sample, you can learn about chemical, spin, magnetic state, relaxation phenomena, and a whole slew of other properties of the system. And this has really widespread applications. I only show some pictorial ones. For example, there is a Mössbauer spectrometer on this Mars rover, which analyzes the rocks on Mars. You can do fundamental tests because the line width is so narrow that you can observe the gravitational redshift over 20 meters the height of the building. And of course, you can also analyze modern materials you find in catalysts, batteries, or for magnetic storage. I also want to show you an example that actually a lot of times then it's really used as a tool. So I'm not involved at all in this work, but I find it quite fascinating. What these people want to do is they want to study superconductivity in hydrogen sulfide. And this substance becomes superconducting at very high pressure, 150 gigapascal. So now the question comes up, how can you verify it in the experiment? Because in order to get this pressure, what you do is you take a diamond angle cell and put the sample in between and squeeze very hard. And that restricts the sample size, in this example, to around 30 micrometer. And then under these conditions, it's very hard to use conventional methods to detect whether you're in the superconducting state or not. So what these people did is, it's a bit hard to see, so the blue substance is what they want to study, and they put one of those Mössbauer nuclei, it's tin in this case, in the middle, and they applied a magnetic field. So now the magnetic field leads to a splitting of the spectrum, and if you then shine broadband light, because you have different frequencies, you observe a beating in the signal. No? And this is just the intensity as a function of time, you have a beating. But now if you take the system in the superconducting state, the magnetic field is expelled out of the system, and that means that now the Mössbauer nuclei do not see the magnetic field anymore, so we have no splitting, and the beating goes away. Yeah? And here you can see that even though the nuclei have nothing to do with the physics under study, it's really a very useful tool in order to see what is going on. So my primary background before I started this nuclear physics was actually quantum optics at visible energies. And the funny thing is that if you now compare what is being done in nuclear physics, or with these Mössbauer nuclei, it, in my view, more relates to the history of the field. It's, for example, Bunsen and Kirchhoff, who actually in Heidelberg put some chemicals to the flame and observed the coloring, which is, of course, a starting point for spectroscopy, because from the coloring you can see what substance you have in there. So what they did is, they took maybe the strongest source around, which was a flame, excited their sample, and looked what happened. And this is what you do with the synchrotron nowadays. Yeah? And if you then think about the next 150 years, of course, there was tremendous development, which means that now you have, in essence, quantum control, at least over simple systems. And this progress was enabled by laser development, coherence, of course, theory development. And the question we have now, why don't we have this at X-ray energies? Yeah? And it's actually not so easy. There are a lot of restrictions because we have these extreme energy, length, and time scales at X-ray energies. You have light source limitation, instrumentation limitation, and it's a relatively new field, in particular for the nuclei. But this is what we want to do. We want to take X-ray physics, in particular related to the Mössbauer, and move it a bit more towards this full quantum control. And we think it's the right time to do so because there are these free electron lasers and upgraded synchrotrons coming up, and also Eli maybe in Romania with the nuclear pillar. And we believe it's now the right time because of this development, and that you actually have to do it in order to exploit the light sources, which are not exactly cheap. So if we manage to do it, it will be a new tool in X-ray physics. This will in turn help us improving or developing the applications I mentioned. But on the other hand, it's also a new platform for quantum dynamics in general with very new properties. So now this sounds quite nice, but of course there are some challenges we have to deal with. And the most severe one is quite interesting because I told you that all the applications are related to the very narrow line width of the nuclei. But this in turn is the strongest problem because the X-ray sources are pulsed and have very short pulses, picosecond to femtosecond or even less, at 3 electron lasers. And in turn it means that their spectrum is very broad. And I drew a cartoon here, so the red one is the spectrum of the X-ray pulse, and then, I mean, it's actually in reality much thinner, the nuclear resonance. You see that actually most of the photons just go straight through. They are just the background because they don't interact. And in turn, it means that we have only a low driving field, and since we have, in essence, only one frequency available at present machines, You don't have control fields or any of the fancy things you would have in any optics lab nowadays. And that means we cannot simply reuse what we know from optical fields, but we have to develop new methods taking into account these practical constraints. And motivated by this, we actually search in two directions. The one is whether we can actually improve the X-ray pulses delivered by these machines, and whether we can get some control over nuclear dynamics, in essence, without control fields. And this is what I want to tell you. So it's here the result of the first part in a nutshell. We take the spectrum of the X-ray pulses delivered by the modern sources, which in a small frequency range around the nuclear resonance is just flat. And only in this small part you will have an interaction, and the rest is just the background. So we thought, wouldn't it be possible to just remove something here and shovel it onto the resonance? Because then you just remove background, which you don't want to have, and you increase actually the intensity of the X-ray pulse behind your sample, and then you can actually do better the actual experiment you want to do. And the way we do it is actually that we first impose an absorption line by just putting nuclei into the beam, and then we apply a magic trick in order to get what we want. And I will show you that if we succeed, it will actually, on the one hand, increase the resonant intensity, but on the other hand, also demonstrate a way of controlling the light-matter interaction. So in order to explain to you how we actually did this trick, I have to remind you how the absorption works like. So this is a cartoon of the experiment we did. The X-ray pulses come, and they hit a foil containing these Metastable nuclei, and then we just look at the spectrum of the scattered light. And then if you look at it, each X-ray photon can do two things. It can just go through, so to say, zeroth order scattering, and so you will have in essence a copy of the is that it interacts once or multiple times with the sample. And this I denoted by the dipole response in the simple case of the sample. And then if you take the spectrum, these two contributions actually destructively interfere, like in the optical theory, and this gives rise to the absorption line in the spectrum. So the picture I have here is the intensity you measure as a function of frequency, and it's normalized to the input pulse. And you first of all have a bit of electronic absorption, and then on top the nuclear resonance. So now, since it's interference that gives rise to the absorption, we thought, wouldn't it be possible to modify it? And it is, in fact. And the way we do it is that we put the iron onto a piezoelectric transducer. And what we then do is that immediately after the X-ray pulse has passed the sample, so the zeroth order is through, but all the excitation that gets scattered is still inside the sample. In this moment, we suddenly shift the sample by half a wavelength of the X-rays. And this turns, in a nutshell, the destructive interference into constructive interference. It's a bit more complicated, but what really happens is that the absorption line turns into a gain line, and if you analyze it, you see that in order to satisfy energy conservation, you remove another part of the spectrum. So now this is quite nice, but it's not so easy because you have to do sub-angstrom motion in a nanosecond timescale and control this. But it turns out that it's possible. So we developed a theory and the instrumentation and then performed some experiments. And here you see a typical experimental hutch with Kilian, who was here, I think, at the last conference. So that's the pipe where the X-rays come out. The sample is placed, and this is already part of our detection system. And the way we do it is that we take, it's a simple version of the sample, a plexiglass holder, and we put the piezoelectric film on top of it with the electrodes in order to drive it. And this small piece here is just a piece of iron which contains the resonant nuclei. And then we drive it with an arbitrary function generator, characterizing the motion, and we synchronize it to the incoming X-ray pulses. So these are results. Sorry. So first of all, we measured, of course, without motion. And this I show you here in this picture. It's again the spectrum, the tuning against the spectral intensity, and the black line shows you the spectrum we recovered from the measurement without motion. And you see it's just two absorption lines, and it's two because we in fact have a magnetic splitting in our sample. So then we performed the motion, and we were able to recover it from the measurement. And this is actually the motion as a function of time. Time is in nanoseconds here. because the pulses, they repeat every 170 nanoseconds roughly, and you see that we really get, immediately after the pulse comes, a more or less sudden jump, and then it stays more or less constant. It's not exactly, because it's actually hard to really control what the piezo does on the scales, but it works very well. And really you see is roughly half a wavelength, 0.4 angstrom scale that we're talking about. And if you do this, and move, for example, to this side, then you see really that the absorption line turns into a gain line, and it's actually taken from here over there. And this you can also verify by just moving in the other direction, and then you see that you again get a gain line, but you move from the other side to the top. And so the gain we achieved there actually overcompensated all loss channels, which means that behind our sample the resonant intensity is increased. And there's ways to increase it even further. So with one piezo you can get approximately a factor of 10. It's limited by the electronic absorption in the sample. And the factor of 10 is quite remarkable because when the last Proton source was opened, it actually had a factor of 8 improvement over the other one in this nuclear resonance. So that's already significant. And we can also take several piezos. So here we, for example, took 2 to even increase it further. And this we demonstrated here. We used one piezo to shovel from the left onto the resonance and one to shovel from the right of the resonance. And this is shown in red and blue. And you see the green curve is the combination of the two which clearly exceeds the two single ones. And of course we work on improving this further to get a maybe user device even that could be deployed at a super radiation facility. So this is all nice, but the question, of course, if you have this new light source, what can you do with it? And one thing that immediately comes to mind that you can also reinterpret what we did. Because what we do is that we take a single pulse and shape it into a double pulse. The first pulse is the light going through, and the second pulse is that what was scattered. And now with our piezo, we can modify the second pulse. We can change the detuning, we can give a phase shift, we can introduce a chirp, just by controlling the motion of the particle. And it's all coherent. And so the question is, can we take this controllable light source and maybe control nuclear dynamics with it? So we can maybe take the nuclei in the ground state, hit it with a nuclear target, and then, for example, the first pulse excites it. And then depending on the properties of the second pulse, we can perform motions on the Bloch sphere, and in principle also reach complicated states of the system which are not available otherwise. So at the synchrotrons, at the moment, we only are in the low excitation regime. So in the proof of principle experiment, we more or less operate at the south pole of the Bloch sphere at very low excitation, but still we can test what we want to do. And so instead of the pictures here, I just saw the view from the top onto the Bloch sphere. So this is the ground state, and the first pulse excites the system. And if you then take the second pulse with the phase, the development or the evolution of the system goes into wherever you would like to have it. So in order to demonstrate this, we want to choose 2 extreme cases. And one case is the one where you have something like a stimulated emission of an exciton actually. Because what happens is you have really a lot of nuclei, and you excite one out of the nuclei with a single X-ray photon maybe, which is resonant in your pulse, but it's a coherent superposition over all of the nuclei which can be excited. And then, if you have this excitation, we can tune the second one such that it does a stimulated emission of this exciton back to the ground state. And the second choice would be to change the relative phase of the 2 pulses by pi, and then you would have a coherent further excitation of the system. So, with this in mind, you of course have to think about how to observe it. There are 2 options in essence. When you do the experiment, you can look sideways, and then you see a clear signature. I don't want to explain it now in detail, but the problem is that it's a weak signal, because since there are so many nuclei and it's a coherent scattering, most of the light is actually scattered in forward direction. So it's good to look in forward direction, but in forward direction you have the interference of whatever you measure with the light which comes in, so with the incoming pulse. At first sight, that means maybe it's a bit a problem to interpret the data, but on the other hand, since everything is coherent, we can actually make a phase-sensitive measurement and really recover from the data the complex dipole moment induced by the nuclei as a function of time. It's like a homodynamic, self-homodynamic measurement we do on the nuclei. So what is then the signature that we can get? We used a very simple theory model in order to interpret this. So it's again, on a logarithmic scale, the intensity you would expect as a function of time. And there's a naive picture. If you excite the system and you stimulate it back to the ground state, you would expect that at initial times you have high intensity when you stimulate it back, but once it's at the ground state, the intensity would be lower. Whereas if you excite further, because of the further excitation, you have less intensity at the beginning and more intensity at later times. Yeah? And that's this crossover, so, already next slide anyway. So here are the two cases, stimulated emission and excitation boost, and you see a certain crossover. Here, the stimulated emission intensity is higher, and here, the excitation boost intensity is higher. And there are further structures which are due to multiple scattering in the target, because it's a bigger target, but we don't have to worry about it. So we did the measurement, and indeed we saw this theoretic crossover. This is the data we recorded. It's the dots, and together with the fit of our theory, there's an additional modulation on top of it because we have the two absorption lines, and this gives rise to this quick beating in the sample, but in the measured spectra. But nevertheless, you see the characteristic crossover from higher intensity at stimulated emission and lower intensity at later times. Now, when you then perform the data analysis, it's possible to extract the dipole moment that we excited in the system, which is maybe a more clear signal of what is going on. So if you don't do anything, you would expect to excite a dipole moment. This the modulus of the dipole moment is a function of time, and it would just exponentially decay to a certain time scale. So when we apply our control, the first pulse excites, and then in the stimulated emission case, you see that the magnitude of the dipole moment goes quickly to zero and then rises again. And what happens here is actually that the second pulse is so intense that it stimulates to the ground state and then re-excites on the other side of the Bloch sphere. So the dipole moment goes up again, and this we see also in the phase of the dipole moment, which exactly in the 0 point does the phase jump of pi. Yeah? So really you see the clear signatures of stimulated emission and then coherent re-excitation. On the other hand, in the excitation boost, the phase of the dipole moment remains more or less constant, and you see that the dipole moment is increased further and only then exponentially decays. And it takes some time because the motion we can induce is not instantaneous. That's just a technical limitation. So then we wanted to find out actually how powerful the method is. And so what we did is we analyzed the stability of our control scheme. And for this we used a measure that is known from optical clocks. It's the L deviation, and it tells you how stable you control the phase in between the two pulses, let's say. And what you do there is that you have a measure which tells you how reproducible your measurements are in essence, and you characterize it as a function of the sampling time. That means how long you do the measurement. And initially it goes down with square root of t. That's just a statistical argument. If you measure longer, you have better statistics. It goes down. And at some point you would expect it to go up again, and these would be systematic effects, maybe some drifts in your system. And what is interesting is that we actually find that this stability reaches down, when you calculate it into a time, to the femtosecond level, which is actually ultra stable. It's better than everything that has been to our knowledge reported before. And that means that we will be able to really do coherent spectroscopy and coherent control schemes for the nuclei in the future. So what are we planning to do with the mechanical control? As I told you, immediate application would be that we can enhance the resonant photon number. So it means that if we have only a few days of measurement time at such a machine, it may be possible to do experiments which are otherwise not feasible, because if they take maybe days, we can reduce it to hours. We will also be able to measure on smaller samples, and we hope that if we go with the electron laser, that we will achieve nonlinear effects with nuclei because of the higher intensity. We can do coherent spectroscopy, and we hope to make use of this to even get the narrow line width of the nuclei better to use, make maybe Ramsey spectroscopy, and we also have used other motion inhalers to already use small frequency pools of X-ray energies by modulating the nuclei, and we believe that we can improve spectroscopy here. We want to do X-ray quantum optics. I have shown to you that you can control, at least in a basic implementation, nuclear dynamics And we can do it without external control fields. So we can somehow simulate control fields known from the visible, and we want to see whether we can use this maybe to study out of equilibrium phenomena with nuclei. Then related, I showed to you that we can measure the motion of the nuclei on a sub-angstrom scale, and this can be useful also for other purposes, because measuring sub-angstrom nanosecond scale is not so easy otherwise, and we believe there will be applications. We also think we can do adaptive X-ray optics, because the motion corresponds to a strong index of refraction, and we'll be able to do this. And what I find very interesting also as a theoretician is that the ideas we have, or we develop, they are not unique to the X-ray. There's, for example, this group by Thomas Pfeiffer at our institute who implements very similar, even the same ideas also in upper second spectroscopy on hydrogen, and so it's really a general theoretical framework. And finally, then, of course, we hope to improve the mass power applications I mentioned to you also in material science. And with this, I would like to come to the summary. So I have shown to you how we can control light matter interactions at X-ray energies with mechanical motion. And as a first step, we have used it to enhance the resonant intensity available at X-ray sources, and that we are able to shape individual X-ray pulses into tunable double pulses, which are coherent, which allow to control us the dynamics of the nuclei. And I've shown you as a first example that we can switch between stimulated emission and excitation boost, but we believe that there will be further more useful applications in the future too. And with this, I would like to thank you very much.
Thank you. Any question, please? Yeah. Professor Mihailescu. Yeah.
Very nice alternative lasers, of course. Very simple. Okay. So I used to say, I said that the very nice alternative lasers is very simple. But I was there when they met the experiment you mentioned about the band, spectral band, also laser, not it was so large, but in that morning, the power was 3 petawatts. This week is 7 petawatts. Are you able to reach these levels? First question. And the second is more profound. It's called coherent. Which is a proof you can show? Which is a coherence length, coherence time of your pulses? Have you measurements? You have proofs. Okay.
It's actually interesting questions. The first one related to the power, in essence, available to these X-ray sources. And the thing is that in our business, the power that you usually read in the data sheet of the beam length is not the quantity that's really of relevance to us. And the reason really is that
everyone has his way.
The reason is that the power measures the entire spectrum, whereas for us the useful photon flux is only in a tiny resonance. So you actually have to compare the power with...
Professor, laser is monochromatic by definition.
These X-ray sources are not monochromatic. That's just a fact, and you can read it in our books, and I would really appreciate if you could let me answer. So the point is that you have alignment of the pulses by definition. If you have pulse laser sources, then they are not monochromatic. That's just the principle of the Fourier theory. And it's a fact that at these sources you have a very broad spectrum, and only a small line width of the spectrum is actually useful for the nuclei. And for this reason, it's not useful to look at the thing. The second question related to the fact about the coherence, and that's something which is not easy to measure. There are actually people who try to do this. It's a spatial measurement have already been done. For the temporal coherence that we are working on here, it's not so easy, but there are simulation methods, you can do it. And we can actually see from our experimental data that it's possible to have this coherent control.
Have you measured experimentally? Time coherence, length coherence, can you measure?
Like I said, when you see the dynamics, you see that it's actually not possible to get this... Do you want to come front and give a talk, or do you want me to let me reply to your question? Great. So, if you have a look at the dynamics, you see what happens is that actually as an average over the entire experiment, we can control after the excitation pulse whether you excite further or whether you take the excitation down. And if you had an incoherent source, it's obvious that this is impossible. And the answer again is a bit more complicated because these X-ray sources, they are, if you look at the data sheet, they are incoherent. But they are incoherent over the entire pulse width. And what happens here is that we again take a very small part of the spectrum, and the coherence length of the pulse is such that over this small spectral region, you do have the sufficient coherence in order to do the experiments here. And that's also well known in the community.
Enough coherence, but what are the numbers?
Good. No. And next, Professor. Yes. Thanks.
What is the minimal time distances between coherent X-ray pulses at time of experimental?
The minimum distance between the pulses. Yeah. So it depends on the light source you're using. We went to the synchrotron pulse, and in the synchrotron pulse you have picosecond pulses. So if you take the pulses taken from the system, it's a picosecond pulse with around 100, a few nanoseconds you can get. When we do our control, it depends on how fast you can do the motion, but it's typically also on the nanosecond time scale governed by the decay time of the nuclei. If you go to other species which decay faster, you can do shorter. Yeah. But if you go to a free electron laser, they now also operate in systems where you have maybe a double pulse coming out of the free electron laser, and then it can be even 2 femtoseconds, but the two pulses are not phase coherent. So you cannot do this coherent control I mentioned there.
Sorry, is it possible to receive some information about the nuclear spin process using your method? Nuclear spin process.
So like I said, there are a lot of applications where they also measure the spin of the system using the Mössbauer effect. But so far we are doing the basic steps and have not analyzed the concrete measurement scheme, like the determination of the spin, and see whether these type of things can be used to improve. But I mean, if you can measure smaller samples, you could naively say it's an advantage, but of course we want to use it for human control. Maybe it will be possible to prepare somehow the system in a state and do a better measurement. Maybe we can do the spectroscopy better. We're currently working on ways to get the signal-to-noise ratio down in such measurements, and then it would be a way. But I cannot give you now a concrete example. It's what we want to do, but this is what we currently have.
But what we are using the optical method, you can extract big ensemble of the nuclear spins, and you can see what is process.
Yeah, there are many methods. Like I said, I mean, of course, modern experiments usually use actually several techniques to combine to characterize the sample, and this is one of them.
Thank you very much. Now, coffee break. Downstairs. Not more. No time enough.
So please take your seats that we can start the next session. I was asked to chair the session. My name is Susan Shaw. I'm from the Helmholtz Zentrum in Berlin, Germany. We would like to start the session. Madame. So we are already a bit late, but I would like to introduce our first speaker, Dr. Ushida from Japan, and he will show us a new discovery of superlattices inside the perovskite solar cells. Yes.
Thank you very much for introductions. Yes. Bună dimineața. I'm very happy to be here in Moldova. This is the first visit. and most friends for kind invitations. Yes. Today, my background is chemistry, not physics. I'm sorry, but I try to do my best. My topic is photovoltaics, solar cell, and especially the most recent issues, so-called perovskite solar cell. Before the perovskite, I just want to show a couple of slides, the history, how the solar cell appears. This is the origin of solar cell. This is not the p-n junction silicon, but wet type solar cell was firstly reported in 18th centuries. Yes, at the time, two platinum electrodes were dipped into the salt, and sunlight was irradiated to show the photocurrent. Of course, performance is not so high, but after that, so many improvement was carried out by using, yes, colored solution was examined to harvest the sunlight. It's reported in 1968 by German scientists. And after that, it's slightly improved because we don't need a color for solution for all bodies. Here, we stained the reddish dye molecules onto the zinc porous semiconductor. And then, yes, this was 1967. And then there are big breakthrough by Professor Goetzel in 1991. He selected to the combination with porous nanoparticle TiO2 sintered electrode with specific ruthenium complex biomolecules to give over 7%. Yes. So at the time we recognized this is real solar cell. Yes, this is one example for dye dipping procedures. To be honest, any kind of dye molecule is available. Yes, and okay, no need to explain for you, all of the scientists. We have a similarity for photosynthesis with having three key components with harvesting the sunlight by using dye, and charge separation must be occurred in the inside the cell membrane. And also inside the membrane there are a kind of electrolyte. We have the same constructions with dye, TiO2 with electrolyte. This is the cross-sectional view with of the device with the glass-to-glass sandwich device. In one side, there are nano TiO2 was attached, about thickness 10 to 20 nanometer, 20 micrometers in thickness to harvest the full sunlight to enhance the surface area, like a sponge. Yes. Anyway, after that, not after that. Yes, as I mentioned before, we have so many options for staining dye molecules. This was invented 2004. Yeah, with me, the collaborative company. Yes, by changing the dye moieties, we can tune the colors. Yes, I just show one example how to assemble the solar cell. Yes, this is a screen mesh. Yes. Like a screen printing. And then we roll the TiO2 paste, and then machine, in this case, designed. And after sandwich, after sandwich, we infiltrate the electrolyte, and it works as a solar cell. It's amazing technology. And this is machine. We roll the acrylic resin for outside to draw the lines like a chocolate. And then electrolyte was dipped very accurately. Yes. The robotics arm can fix the substrate inside the chamber over there. And this is lower substrate and fixed face to face, and the air was evacuated to remove out and pushed face to face. And finally, yes, we have to give a strong UV light to cure the resin to seal. And then finally, the solar cell comes appeared. This machine was constructed by our laboratories a couple of years ago. This is one example for high performance, and we have so many options because screen printing is free for design. We can assemble any kind of patterns, this way or that way. Yes, in 1915 maybe, the French president visited us and we gifted a specific designed solar cell for him. Yes. For these activities, yes, Dr. Kojoko strongly supported us because she always stood in front of us because she was very nice research scientist. Yes, so many people, not scientists but also students or politicians visited us to see our kind of prototype machine. Yes, always, yes, she explained how to assemble the dye solar cells. To be honest, this is my first contact with Moldovan scientists. Now is opposite. Maybe some of you are first to see the Japanese scientist here. That's why I am here. Okay. Yes, she did a very nice research work and have a result. WCPEC is one of the biggest conference, international conference, and among the students talk, she won the Young Researchers Award. Very nice. Okay, let's turn back to the perovskite solar cell. The people are very much attracted. Yes, okay. The name perovskite came from the mineralogical classification you know very well. It's one of the name from the Russian perovskite's name. The people mostly know calcium titanate or barium titanate. In our case, yes, the A side cation is a kind of organic molecule, not inorganic. Yes, so we can recognize these device materials are kind of hybrid inorganic organic materials. Yes, as I shown before, the structure started from the dye solar cell with having thicker nanopolar structures here with liquid electrolyte. And after that, for improving the whole conductor was examined. Now here we are using the kind of spiral, so-called organic molecule was used, and the thickness became less than 1 nanometers. Finally, the structure became like a PN junction stacking simplified device. It's amazing because this is a history of the progress of the solar cells. Sorry, it's too small, but in any kind of solar cell, normally the trend is the following: 0.3% per year in the average. But the perovskite showed 10 times higher progress than any other solar cell, and already beyond the multicrystalline silicon solar cell, more than amorphous solar cell, and beyond the cadmium chamberite, beyond CIGS. Yes, it's amazing in progress. Nobody expected organic photovoltaics can beyond such kind of variations. And still going up, even now. Okay, this is today's my topic. Yes, we found a specific character inside the perovskite, and I show you the next slide.
Photovoltaic technology has come a long way, reaching higher power conversion efficiencies than ever before. Recently, organometal halide perovskite has shown remarkable results in solar cell application. However, little is known about their microstructural properties that give rise to their remarkable performance. In a communication in advanced materials, University of Tokyo researchers Taewoon Kim, Satoshi Uchida, and Hiroshi Segawa and their co-workers investigate the structure of the organometal halide perovskites, a ubiquitous class of solar cells.
Until now, it has been believed each crystal phase of the perovskite solely exists at its given temperature range. However, in this research, we revealed that crystal phases coexist at room temperature, and the coexistence induces self-organized superlattice structure. These evidences overturn the conventional theory, especially the existence of the spontaneous superlattice will maximize their potential for wide and diverse applications.
The authors used transmission electron microscopy to elucidate the structure of the perovskite layer in a methyl ammonium lead iodide solar cell. Unexpectedly, this
Okay, I explain one by one. This is cross-sectional view of the perovskite device. The red part is the main light absorber of the perovskite, with having chemical formula CH3NS3 PbI3. Yes. It is sandwiched with the TiO2 dense compact layer for bottom, and upper side there are so-called spiral Automata, is low molecule pole conductors. Yes. We recognize this device so-called PIN constructions. I don't know if it's true or not, but anyway. The thickness is arranged less than 1 micrometers, very thick, one of the thinner photovoltaics. And this is crystal structures. Normally, the people discussed, okay, at the room temperature, the phase must be exist as a tetragonal phase and flexible against the temperatures. At the higher temperature, it shows that it changes in the cubic, but to be honest, the difference is very small. I show you. Yes, and this is true, but not true in our thin film. Yes, this is our new recent findings. This is a illustration of the tetragonal solar cell. Yes, from top view, you can see a bit shift tilting angle from the top first layer and the second layers, slightly shifted, and side view is the same. Yeah. This tilting angle is flexible against the temperatures. At the higher temperature, the unit cell expands a little bit, and then the angle becomes smaller, and after reaching over 55 degrees, it perfectly overlapped, and we recognize the cubic. Yes, that sign of trend is reversible. So, from conventional X-ray analysis by pulsar diffraction patterns, it's hard to distinguish because of the small difference. This is computational drawing by tetra to cubic. There are no very less differences. Yes, there are small minor peak should be appeared in the case of tetra, but yes. But yes, you can find out. Suppose this is computational estimation. The most of the X-ray pattern came from the reflection from the PB atoms, elements itself. That means, okay, let's show you. Let me allow to show you again. Of course, the position, location of the PB, iodine shifted a little bit. But most of the signal came from the PB element, and the location don't changes with cubic tetra. That's why it's hard to identify which is which in the practical situations. So to overcome this kind of difficulties, we try to use the very specific TEM analysis with the FIB processing. From top view, I draw the line on the screen and then give a gallium ion beam to dig the ground, and then pull out by attaching the nanoprobe and pull out the sample specimens, and then put into the copper mesh to attach for 10 TEM mesh, copper mesh. And finally, we slice and scratch in the range 100 nanometers for thickness to make a very fine samples and put into the TEM. For these activities, I thanks to Hitachi people, they supported us very much. And then, this is one typical TEM pictures. The degree of the crystalline is very, very nice. Yes. For any locations, I could see clear, very nice patterns for electron diffraction patterns. And if I carefully observe the surface, we could see so many twins on the surface. Some people recognize this is a kind of evidence of the no damage as it is observed. And this is the change of the spots. In case of a cubic, because of the higher symmetry, there are less spots. But in case of tilting the angle, we have additional red spots. By this way, we can distinguish which is which. Yes, this is one example. In the same same materials, same condition, same time, film was constructed, but we found so many differences. Phase coexistence with tetra to cubic. Yes. Furthermore, I found superlattice. What is a superlattice? But by stacking the tetra to cubic something, by stacking sequence, sometimes the triple TCT makes long range intervals to give a long D spacing. Yes. With having, yes. We could see clearly for here, for example, there are long intervals to form the superlattice, and additionally, we could found so many multicrystalline with ranges 10 to 15 nanometers. Nano-sized grain was formed. We recognize this is a kind of multicrystalline. To be honest, I don't know at this moment how it forms. Some people may consider the spinodal decomposition or not, but we need more science for analysis. And I think the reason, one of the reasons why the perovskite solar cell gives showed a very high performance, due to the existence of the superlattice. It may contribute to the charge separation theoretically, yes, without having collision of the electron and hole. And it locates not only for bridging cubic to tetra to cancel the small distortion of the lattice mismatch, but it locates sometimes with TiO2 and nano around the perovskite. This is the estimation. at a higher temperature, yes, we put the, after dipping the electrolyte, we put it into the hot plate to heat, to make a perovskite. At the time, the phase must be cubic, but during the quenching, minor portion of the cubic is freeze, still remain inside the lattice, maybe. And theoretically, suppose the first layer is tetra, the second layer have an option tetra or cubic, and finally, after 5 stacking, theoretically, okay, 40% came from the will result in a single phase, and still big portion is having a double superlattices. And this is real observations. Yes, it is just accepted. About 58% were shared by tetragonal. The next big portion is tetra or cubic double superlattice. Anyway, yes. And before I finish my talk, I just mentioned a couple of slides for something related with physical applications. It's application for nuclear battery by using perovskite solar cell. What it is, yes. The idea is not new, yes. Some people have already examined. Normally the people give the sunlight to power generation for solar cell, but some people can try the radiations. You have a choice, alpha, beta, gamma, or even for yes. And then we are using the PV compound and should absorb the gamma radiation. To be honest, I'm not the expert of this kind, that's why I'm very much welcome for your support or advice if you have a more deeper science. Yes. This is one example, not a perovskite. Gallium ion phosphate indium was examined to harvest power generation by alpha radiations. PN junction solar cell, yes. Very small amount conversion efficiency, but it's already proved. And the gamma radiation for perovskite was examined, but it's suspicious because I tried by myself, and the background is hard to. It's very suspicious. Yes, yes. I tell you because. Okay. For this experiment, I bought the radioisotope standard source with color 60 and cesium-137 as a for example. Both, yes, diskette give gamma radiations with different energy levels of voltage. Yes, and then 3 years ago, the sample was delivered to me. Yes. The radiation level is, anyway. And to be honest, the power generation was unclear. At the beginning, I disappointed. But finally, I understood because the gamma radiation is not a continuous flow, energy flow, but a pulse with irregular, natural occurred pulse. That's why the slow IB scan cannot catch up the true power generations. That's why I changed the analysis by using so-called maximum power point tracking system, MPPT, with quick detection of the power generations and accurate to keep always the Pmax. And then, yes, maybe it can be stabilized much better than IB scan. And finally, yes, we found the power generations. Very small photocurrent, not photocurrent, gamma voltaic current with 108 picowatt. But it exists. And then, now, we had a big disaster, terrible accident in the Fukushima area 7 years ago. Still a bit higher radiation is the land was polluted. Yes, year by year, the level of the radiation became less and less, but still exists. The terrible thing is inside the nuclear power plant, collapsed one, still have a very high level of radiations with having 530 sievert, not micro. Yes, and from our result, I can estimate our perovskite solar cell can generate 954 watt for 1 square centimeters. Of course, we can stack the device to improve the performance, but it's a bit higher number, I believe. And I'm sorry, I don't have a good conclusion, but I think it's almost time to finish my talk. Yes, thank you very much for your kind attention.
Yeah, thanks for this talk, which is now open for discussion. I see already 4 questions, so we start here and then we go.
Thank you for nice presentation. What do you mean when you speak about thin layer? What is the thickness? And related question, if you decrease this thickness, if you go to ultra thin films, will it change the ratio between different crystallographic phases in your system?
Okay, I understand. So thickness is now the red part, the perovskite is 500 nanometers, something around. It's optimized. Yes. If it is thicker, we lose the voltage and the performance. That's why the 500 nanometer is the peak for our device. And that thickness is the thinnest among all the variations of solar cells. Yes.
Yeah. Okay, thank you.
Who was next? There are some questions.
Thank you for presentation. Also the technical question. And what about the resistivity at the room temperature of this perovskite film?
You mean as an electronic circuit? Maybe
the resistivity at room temperature of this layer?
It ranges about 200 kilo ohm, something around. Yes, yes.
Ushida-san, I have only one question. I think one of the more important parameters for perovskite is the temporal stability of your structure. Temporal stability under the light illumination. What can you say about the parameter in your structures?
Yes, it's a very serious issue. And chemically, after more than 130 degrees, it decomposes. Yes, and finally, the organic molecule, methyl ammonium, goes out to decompose into the PbI2. But at least in the nature, in the Earth, like less than 100, the material itself is stable. But we need a sealing because it's very reactive with the moisture in the air. That's why some perfect sealing is essential. Yes.
Maybe my question is very generous, but you talk too. We always interested in finding more energy in electric energy, taking solar energy. One of the ways to increase this is light harvesting,
yes,
as you mentioned.
Yes.
And this is one way for improving of perovskite solar cells. Could you make any comments about scattering? I'm sorry, scattering in such a field. So one of the way of scattering, of the way of harvesting, improving harvesting is scattering.
Yes.
And depending on this value, yes, we can maybe possible to say drive the amount of scattered light if we are able to organize properly the structure.
Yes.
And which structure? it's a question too. Because it can be not only a structure of semiconductors, it can be maybe neutral values, something and something else which is able to increase scattering to get more amount of scattered light inside the cell, and this is owing this fact to increase absorption and the output. Thank you. I'm sorry.
Yes.
A long question.
Your point is quite right. The loss of the scattering for reflection on the surface is ranges maybe 4 or 8%, something around. Yes. And to harvest that kind of scattering light, some people in the higher competition, in the world records, we use a kind of anti-reflecting coating with having most eye constructions, or yes, that improve the additional a couple of performance. Is that okay?
I think because of the time we have to move on. I'm sorry. There are more questions. Maybe the last one. The last one.
Thank you, Professor. You speak about top performances. So we go to market. Market means lifetime. So it was a question before about chemical stability and something about the temperature stability. I will ask you about time stability. How long you can trust your cells?
Yes, you are right. At the early stage of our experiment, we have a terrible poor lifetime. Even for the evaluation IV scan in a minute, yes. It was decomposed. No. But after that, now the people don't pay attention so much, not serious, because well protection of the surface is already proved more than 10,000 hours, something around. Yes, much more. Yes, practically. Yes.
Thank you.
Okay, now I think we have to move on to the next talk. Thanks for I will hand over to Dr. Proton, who is sharing the session.
Our next talk, our next reporter is Professor Nicole from Switzerland. Please.
Thank you for the introduction, and I would like to thank the organizing committee for the kind invitation to come to Moldova. Thanks a lot. I will bring a molecular impression to the audience, a molecular world, about the molecular world. And it's about a molecular world in a confined environment. Confined means can be two-dimensional on a surface, or it can be one-dimensional in a junction. For this talk, I will focus on the two-dimensional case, on the molecular world on a surface. But I think it's appropriate for this slide. It's almost self-explaining, this slide. I would really like to acknowledge the long-standing collaboration we had in a program between Moldova and Switzerland now for 15, maybe even 20 years, especially with groups of Professor Svetlana Bakker, Professor Sofia Kroknischer, Professor Kravtsov, and the teams, the team members from the Institute of Applied Physics. It was a wonderful time, and I really hope that with the new program which will come around soon, that's the National Science Foundation, that we can establish a new program with the teams again. We have to discuss during that week this issue. I have some information. So let's hope for this. And the picture you see on the left side, we studied wonderful molecular clusters which have been prepared in the laboratory of Victor and we had I could admire a wonderful theory, for example, on spin-crossover compounds, which was theoretically investigated by Sophia Kotnifer and her team. Thanks a lot for that. Next slide, please. So, for this agenda, our collaborators are from physics, from experimental physics, the team of Professor Yashareb in Regensburg, Germany, Ernst Meyer, University of Basel, and Thomas Jung at PSI Switzerland, and Dr. Leo Gross from IBM Switzerland. And for theory, we see the teams of Professor Colin Lambert in UK, Pavel Jelinek from Prague, Peter Oppenier from Sweden, and our colleague from Madrid, Spain. This really a situation. This study can only be done if chemistry and physics comes together. It needs both. Physics alone cannot do it, chemistry alone cannot do it, but together we can achieve some progress. And this is the aim of this talk. We go to the next one. And we could also say it's about on-surface chemistry. We see here some molecules. On the left side, a DPD type of molecule, which has a special conformation. The nitrogen are on opposite sides, but when one offers, for example, metal ions like iron, you see the conformation switches towards this configuration. That's a study which was done with the colleagues in Basel. We can also say it's a matter of numbers. As chemists, we are used in the lab chemistry to deal with, let's say, 10 to the 7th power of 17 molecules to study luminescence or whatever. That's normally what we think about chemistry. However, if we go in a confined environment, like in a junction, one-dimensional, we speak about one single molecule which we measure. Of course, we make statistics, we can measure it 1,000 times, but each time we make one. And if you go on a surface, we may measure, look at it, investigate one or a few molecules. So, we will deal now with the right side. And of course, in physics, we need ultra-high vacuum conditions to study the systems, and we need STM, AFM's scanning probe microscopy technique to image what happens on the surface. That's an instrument at the University of Basel. And chemistry on a surface means reaction mechanism on a surface. And I show a prototypical reaction. It's a so-called Ullmann reaction. Here, in this example, on a Kepler 111 single crystal surface. And I took an example from the literature, from the Schirmeisen group from Germany. And it's prototypical. Ullmann reaction was discovered or described in chemistry. It was about 1901 already. But it's in bulk, in solution chemistry. Now one tries to apply it on a surface. And what happens typically? Here we see a triphenyl type of molecule to the left with one bromine substitution. And if you heat it up, let's say around 200 Kelvin on the substrate, it will be evaporated on the surface, it sublimes, and it's deposited on the surface. We can image it, and if we heat it up, the bromine will go, and a radical intermediate will be here. One can image, one can study it. If you go even higher in temperature, there will be, again, an intermediate step, a metalloorganic compound, where a copper atom, and there are many copper atoms on a surface floating or at edges, will form units, and if you go even higher in temperature, around 500 K, you form now, you make the chemistry, a new molecule. So that's a typical case about Ullmann reaction. First example, the molecule also, as a coordination chemist, if you look at such molecule, you will say it's a ligand which binds metals. It's a bridging ligand, and of course it can be done like this example. It works as a ligand in normal coordination chemistry. We are not interested now in the nitrogen sites, but we see the next slide. we are interested in the carbon-hydrogen bonds, left side. And we see we have on left two different types. We have the CH bonds on the pyridine rings, and on the right, which is marked red, we have the CH on a pyrazine ring where we have two nitrogens. So they are different. And we know from literature, from Scholl, old Literaturebericht der Deutsche Chemische Gesellschaft, 1910, about the Scholl reaction where you can, in Vulcan solution, form new CC bonds. And for example, perylene is made from merging two naphthalene units. Now comes the scientific question. Next slide. The scientific questions here are, suppose, can we do on surface and CC bond formation, allyl bond formation, for example, on a gold 1,1 crystal? And does it matter which CC bond are formed, on the pyrazine or on the pyridine side? That's a scientific question. So we do it. Next slide. And we put it on a gold 1,1 surface, heat it up, anneal it to room temperature, and we see the single molecules assembled together, not yet CC bonded, but it has a CHN hydrogen bond. No one can understand it, this assembly, and understand each type of assembly on this. So, what is necessary to proceed? One has to get to higher temperature. Next slide. So we go now to 410 Celsius. And now it happens. I take one example, the D2, it's a diamond, and you see to the right here, two molecules merge, they form a new CC bond, and one can image it, and one can see which C reacts, and to the right you see it's one carbon from the pyrazine below and one carbon from the pyridine. So you can investigate, you can look at it, you can now make a chemical reaction and look at the chemical reaction on the level of single molecules. You can study all these kind of assemblies or new molecules you see, and for example, in one, again for a dimer, sometimes there is a gold atom included in the chelating site. One can see when it is in, when not. One sees, for example, tetramers. The question is it a tetramer like the I there, where we have simultaneously bound CC bonds, but in fact, the detailed investigation shows no, it's a dimer of dimers, in this case. So one can go on, and here I want to show that the colleagues from Zurich, was Pavel Jelinek in Prague, they can simulate the AFM picture, they can simulate what happens, and it gives us a deeper insight into the situation, for example, if gold is added or gold is not added. The outcome of this study, the next slide, we studied 160 newly formed CC bonds. It's on surface chemistry, and we observed that no coupling between pyridine atoms and carbon atoms occurred on the left side. Most pronounced was a real coupling between pyrazine and pyrazine. So, why it's getting up? Oh, now we have to go back. It's about getting experience on surface chemistry and employing selection rules. It's catalysis, finally. Catalysis at the level of single molecules. So we get a deep understanding how catalytic processes works. That's an important step. So, knowing that the pyrazine group is important, now comes the next. Of course, it's obvious that we go to a molecule, a different type, where we have three pyridine molecules. So, the study is ongoing. I'll show you where we are. Next slide. We are able, with a colleague in Regensburg, now with Serge Rep's group, to assemble them. We can study the assembling. It's not yet CC bounded, but it's an assembly, an amorphous assembly. Next slide. We can also observe transition from amorphous to crystalline phases now on a single layer of molecules on this basis. So that's ongoing work. Next step, of course, is then to make covalent networks. With the Nossa system, we are a bit further. And here I want to show you that there are so many possibilities about precursor molecules. Look at the left side. The backbone is like a pentachene molecule but it's a tetraaza pentacene. We have 4 nitrogen. And we have the bromine positions on the situation as you see it here. And if we make now this zip coupling on a surface, in this case we get a very nice carbonate type like this. Huh? It's a monolayer, huh? Atomic thick, 1 covalent bound carbonyl like this. If we take a bit another kind of precursor, the bromine are now in a particular direction, it forms ribbons. And we end up with a porous graphene nanoribbon, endoped, atomically precise. So it shows us that where is the limit? The limit is in our creativity, how to make precursor molecules. To get it done and tried out. Second example, perylene. We already have seen it. Fusion of 2 naphthalene units. Perylene is well studied. But we made a modification. We put 4 nitrogen of perylene. So it's a tetraaza perylene. We call it tape. Now, this molecule, next slide, a chemist would again say, it's a breaching ligand. We coordinate metal ions. This can be done, yes. That's solution chemistry, coordination chemistry. But we want to do something on a surface. Now, let's take tape on a surface. Next slide. And we can think about how would it assemble. If we know direction, the forces are important, that CHN hydrogen bonds, we would expect something like that. We see this right, I guess. Of course, in a bulk phase, the pi bistacking will dominate the crystal structure. But on a surface, we expect something like that. Huh? Now we see what happens if we put it on a silver surface. Next slide. And it does so. Huh? You see the silver one on one surface. The molecules are deposited on top of it. Submolar layer, we see a very nice regular assembly, as we expected from the hydrogen bonding pattern. Very uniform assembly on a scale of 1 nanometer square. Now, if we have such nice assemblies, we would like to put functions into it. Now, if we look at the periphery, at the edge of the island, we see an alternation. Gray, white, gray, white, gray, white in the image. It means the molecule has different charge states. In the bulk and tape R molecule, we call it A, gray. And always, if at the periphery the molecule exposes the nitrogen to the edge, it's less negative charge. So it's, we have 2 numbers, 0, 1. Charge, not charge, on the periphery. Also in this very high resolution AFM picture, we see the situation at the edge, type Q, type A, type Q molecules. Now, of course, if we make a more negative bias on the silver template, also the Q-type molecules will get charged, as we see on the left side. Or you can go with a dip on top of a Q molecule, and with a dip you can charge it, and you can see at which sample bias a Q molecule will be charged by the tip. So, knowing this, observing this, we go a step further, and we think if we take a molecule out of the assembly with a tip, we create an internal free space. And what we could expect and what happens, the neighboring molecules switch to Q. That change the charge state. So you can pick out by will molecule and you can switch the neighboring, but only these 2 which expose the nitrogen side to the vacancy. Next slide. And now you can play around. You can make now in a very regular pattern on a 1 nanometer to 1 nanometer scale, you can create charge patterns by control and by will. You have a memory, you have a situation where you have 0 1s on a nanometer scale. Very robust, very stable. And of course, the environment, if you go with a dip on a Q molecule and you charge it, the value, the threshold value of the bias voltage where you charge it depends on the neighbors. And it leads us to the concept of quantum cellular automata, where you have cells, and the outcome of a cell depends on the outcome of the neighboring cells. So conceptually, it goes into that direction. The third example, it's about, I'll show you possibility how to make polymers. We take a pyrene molecule, left side, put 2 bromine on the edges, and then Ullmann reaction, we learned it, you apply the Ullmann reaction, you can form polymers on the surface. And you see in the picture in the middle, you form beautiful polymeric strands on the surface by that method. And now I have to go one back. And you see where the blue arrow is. If 2 strands come close together, you can merge them, you can fuse them, and you get carbon-based graphene nanoribbons by fusing 2 chains together. So there is a lot of stuff into it. Our colleagues at the University of Basel, they are interested in friction study. To study friction on the nanoscale, mechanics. And they took one example with 35 units of the pyrene in the chain, and they can lift it with a tip, drag it on the whole surface, and study the frictional behavior at the nanoscale. It's mechanics at the nanoscale. Next slide. They see the frequency shifts of the tip, they can translate it into forces, so they can study the force, and they can study the traces of the polymer if they pull it over the slide. And they see 2 coexistent periods, and by theory, they can, by simulation, they can understand it. This here is more a little movie. Let's try. It's a simulation about this process, which helps to understand the behavior if you drag such a polymer over a surface. It goes to the basics of study nanofriction on a single molecular level. And they understand why it's snake-like behavior, because it has to be in the registry with the surface, with the orientation of the surface. Finally, in all the examples I showed you, our colleagues in physics say sublime the molecular systems on the surface through the gas phase, with the solid gas phase interface. Now, this gives us limitations for the chemistry, because we cannot take too large, too complex molecules, because they will not sublime or they will fragment during that process. But one knows from mass spectrometry that you can inject in ultra-high vacuum chamber molecules through the electrospray deposition. So it's also possible to do it in an ultra-high vacuum situation. And this is proven here. And next slide, we had a proof of concept just beginning of this year, when we took very complex molecules which we synthesized to the left or to the right with longer cool chains and with sulfur, with oxygen, with nitrogen in it. And we could show that by this technique, we can now get almost any molecular precursor, any molecule clean on the surface, and they stay intact. Of course, this opens now many possibilities for our creative chemists to make nice precursor molecules, complex one, put it on the surface, and then we start to make the on-surface chemistry and to study catalytic processes. This slide is only to show that we work not always on metal surfaces. Sometimes we need to decouple molecules from the metal, and then our colleagues can put 1, 2, 3 monolayers ml of salt, not sodium chloride, on the metal. You can know exactly how many monolayers you have. Then you put your molecules on the salt. You can investigate it, and you have it decoupled electronically from the metal. This was a study with IBM Zurich. And there is a field of magnetism, of course, which I did not touch, where you can put molecules with beam carrier centers, with 3D metals, open shell systems on a surface, on a metallic surface, like we see at the left, a copper oxide surface, which is magnetic and to study magnetism. You even can do it, as we recently showed, on a gold surface, where we realized the first very magnetic monocular monolayer on a surface. Or we even work with molecular crystals to the left side, where the surface is made up of molecules. And we studied, in this case, the assembly of C60 molecules on a molecular surface, and you see the nice islands of C60. So, there is a lot of room at the bottom when chemists and physics meet on this topic. And the credit goes to the teams and all our collaborators, and I thank you very much for your attention.
Thank you very much. Open now questions, please.
I would like to learn a bit more about the role of the surface you have. I mean, obviously it sets geometry, and you also hinted with the soil that it's like a bath. But when you speak about catalysis, does it have a function in the catalysis, or it's all the precursor molecules that decide what you do more or less?
It's a metal you choose, for example. If it's different if you choose gold or copper or silver, the reactivity is different. What's important is which orientation. You have a 100 or a 111. It's very different, the topography of the surface. So both has an influence. And then is the temperature, and then is the reflection precursor surface. Very important.
Other questions?
What about the temperature stability? This self-assembly take places around several degrees of Kelvin.
Yeah.
And the several degrees of Celsius, does this present?
Most of the investigations have been done at low temperature. You are nearly, but then you cool down to image it with the technique, AFM, STM techniques. Of course, if we approach now the CC bonding, and we get these covalent networks, then we have like graphene, we have, for example, end-doped porous graphene networks, or like the Recombination network. They are very stable then. After the chemistry is done, it's stable. We have a single layer molecular network. Yeah, then it's stable.
Dear Professor, I want to ask you about primary, secondary bonds in this chain of molecules, if it is possible, like in protein, for example, in organic system.
You have to ask me.
Primary, for example, primary in protein, it's peptide bonds. Secondary in protein, it's hydrogen bonds. How about these bonds? Have you some classification bonds between the atoms in your molecules?
Hydrogen bonding, for example. Yeah, if we have strands, of course there are studies which we have different polymers, and you study the interpolymer interactions by hydrogen bonds. That's done. On a surface, you have different polymers, and the interpolymer interaction will be mostly hydrogen bonding interactions. Is this a question, or otherwise we? Yeah.
Last question. Yes, present time. Last question.
Okay, you spoke from a point of view of chemists, so I ask you from point of view of physicists. So, using your method analysis, simple analysis, you said put on surface. Is it somehow changing the surface? Can it affect the surface? Can it produce a modification of the surface?
Yes, if you address, for example, the charging, there will be an image charge on the surface.
Only charge.
Image charge, yeah. Well, this comes first to my mind. The charging behavior, that's the most important one. Structurally, I would say less. Structurally less.
Okay.
Yeah, but the charging is very important.
Thank you very much.
Yeah.
Let's thanks the speaker again.
We come now to the last talk in this session, given by Dr. Remska. from Slovenia on low-dimensional tungsten and molybdenum-based nanomaterials.
Hello, ladies and gentlemen. Firstly, I would like to thank for kind invitation. It's the first time for me to be here, and I'm really impressed about the level of the talks and also what I saw from the windows about the architecture in this town. So today I'm going to speak about tungsten and molybdenum-based nanomaterials. Can you hear me? It's okay. It's better maybe now. So the background of this image you see here is called nanoworld. It was done with exfoliation of molybdenum disulfide nanotubes and water dispersion of these single layered flakes dried on the silicon wafer for more than 12 hours. So these monolayer flakes completely covered the surface of water droplet and prevented the dissolution of water. The flakes self-organized on the surface of the water surface. This is just for the fun. So I'm going to speak about the discovery of inorganic nanotubes. Sorry. Many years ago. Unfortunately, at that time, researchers were not interested in inorganic nanotubes. Most of them were worked with carbon nanotubes, and this so-called transition method coordinate nanotubes were put aside. Only a group from Israel and from Slovenia worked in this field. I will present the chemical transport reaction and different new structures synthesized by this method. Here you see some oriented growths of tungsten disulfide nanotubes, molybdenum disulfide nanoonions, molybdenum disulfide nanocubes, just as illustration. So the first inorganic nanotubes in Slovenia were synthesized in 1996. So you see more than 22 years ago. Only a few years after the first report on inorganic nanotubes by Reshevteni group from Weizmann Institute from Israel. What is interesting in these compounds is that they crystallize in two polytypes. In a stable hexagonal polytype and in metastable rhombohedral polytype, which is nearly not mentioned in scientific literature. Why metastable? Because it exists only at pressures about 40 kilobars. The red line of all these materials which I will present is synthesis by chemical transport reaction. This method mimics the natural processes of the mineral growth. Also, the minerals usually grow in a confined volume, confined geometry. We synthesize materials in quartz ampules, which are sealed, evacuated and sealed, and the result of the synthesis will depend on amount of material put into such a quartz ampule, on temperature, on the local conditions of gas flow. So you never really know what will happen when we break the ampule. But exactly this complex reaction enables production of very new materials, unique. So how the chemical transport reaction takes place, we put the material into the ampule. At the hot side of the ampule, here the material, let's say here is molybdenum disulfide, decomposes to molybdenum and sulfur. Molybdenum reacts with iodinum, which is used as a transport agent, and with traces of water or oxygen. These volatile molecules are condensated at the colder part of the ampule, where it becomes unstable, and molybdenum again reacts with the sulfur, which is everywhere in the air tube. So the iodine is only used as a transport agent. The reaction is very long-term, so usually between 1 and 3 weeks. So the material grows from the vapor phase at high temperature. This means the defects are relaxed. The final product contains extremely low density of defects, and some aspect ratio of this material is also huge, as you will see later. So here you see the first pictures from the first report on molybdenum disulfide. It was not nanotubes, they were microtubes. Their geometry were much beyond all theoretical predictions for these materials. So they usually nucleate at the edges of strongly ondulated platelet crystals of the same compound. And when they come away from this edge, they just continue to grow as very long nanotubes. So the lengths are in millimeter scale. The diameters are somehow between 10 nanometers and 10, 12 micrometers. Here you see the widest tube we synthesized. It has 11 micrometers in diameter, only 90 nanometers in wall thickness, and it was long several hundreds micrometers. The crystal perfection is quite good. We realized that the wall thickness depends on the diameter. So in more narrow nanotubes, the wall thickness is between 25 and 30% of the diameter, while in wider nanotubes, the wall thickness is much, much lower than the tube diameter. So the tubes grow together with plate-like crystals. You see only part of them. They are really extremely long, very perfect in geometry. But we did not find any method how to separate these tubes away from the platelet crystals. So for this traditional application to use MOS2 as a lubricant, this was not possible to investigate. So we were searching for another method, geometry, or on the diameter if you have cylindrical geometry. So in narrow nanotubes with diameter below 100 nanometers, the stacking is stable, hexagonal, while in microtubes, the stacking is rhombohedral. This one, which is at a flat geometry, stable only at very high pressures. This means, this indirectly evidences that we have very high strain incorporated in the wall of the nanotube. So these tubes which crystallizes in rhombohedral polytype can be useful for the valleytronics because the researchers recently discovered that the energy level diagram for 2H and 3R polytype differ in this area between K and H points of brilliance zone. And here we don't have the crossing of the levels. So it's possible to store information in these split energy levels. But they need material which would crystallize in rhombohedral polytype, and this rhombohedral polytype would be stable at normal conditions. And exactly these microtubes crystallized in this rhombohedral polytype. So although I report very, very old results, it seems that nowadays they are becoming more and more popular, also this kind of the tubes. Bending of the tubes is an energetically very high-cost process because they usually grow in completely straightforward way. So if they are forced to bend, you see a lot of broken layers in the inner surface of such a tube. So the tubes would would somehow like to escape any bending. And what they do if they meet during the growth an obstacle, they simply flatten. So they collapse into a form of ribbon. Here you see the cross-section of this ribbon, so you see that the molecular layers are not broken. Of course, there is a high concentration of defects at this highly curved structure, but the molecular layers continue to the other side of this collapsed tube. So when the tube collapses, it continues to grow as a ribbon. This is different as in comparison with graphene ribbons, which you nearly must make them artificially. So this is a completely spontaneous growth of MOS2 and tungsten disulfide 2 when it meets an obstacle at one moment during the growth. These structures are completely not investigated still. More than 20 years after the discovery of the first tubes, the first field effect transistors were made out of these structures at Notre Dame University in the US because they realized that they contain very small concentration of the defects, and also the topic became fashion. So they made field effect transistor. They molybdenum disulfide, the tube was on aluminum oxide substrate on silicon. So here you see the cross-section of the ribbon and slightly deformed the tube. And they found very high gate modulation, around 1000 times, when they changed the gate voltage. So this somehow encouraged me to go back again to find these materials, and we continued the research. Just recently, a few weeks ago, it was published a report which was done in collaboration with the IOFA Institute from St. Petersburg and a French group from Montpellier. They proved actually that these highly perfect tubes can act as optical resonators. So when they irradiated the tube with the laser light with polarization along the tube axis, they got peaks in photoluminescence because of this confinement of the light in the tube wall. So the temperature dependence on this micro photoluminescence spectra shows that even close to the room temperature, it's still possible to see these peaks in photoluminescence. So it's somehow a very interesting result, which shows that these highly perfected tubes can be used also as a kind of sensors. As I mentioned before, these tubes prepared with chemical transport reaction are very nice, have ideal structure, very low density of defects, they are long, they have a high aspect ratio, but we can't use them for so-called industrial tests because we cannot have, I don't know, grams of pure tubes. So in 2007, we found out a new type of the synthesis. In this case, we synthesized molybdenum sulfur iodinum nanowires, again with chemical transport reaction. And then we exchanged the iodinum with sulfur in so-called sulfurization process. And we synthesized molybdenum disulfide mama tubes. Did you hear from mama tubes already? It was published more than 10 years ago. So So this is molybdenum disulfide tube with molybdenum disulfide nano onions inside the structure spontaneously grown. And why mama tubes? Because these babies grow on account of material which would otherwise form the wall of the tube. The wall is very thin, only 10 nanometers thick. So if we use another material, another nanowires, tungsten 5 oxygen 14, and we sulfurize this, we got tungsten disulfide nanobuds. In this case, tungsten disulfide nanotube is decorated on the surface with tungsten disulfide nano-onions. So now, as the previous speaker said, it's a lot of different ways for the creativity. So we use different precursor crystals, all were synthesized with chemical transport reaction, and we synthesize different structures. So here you see our laboratory with sulfurization gases. One of the most used geometry of tungsten disulfide tube is this one, which is called coaxial molybdenum disulfide nanotube. So this is one nanotube which has split walls. So it's a tube inside the tube, and all this wall thickness is around 12 nanometers, 10, 12. And you see, they're really huge, millimeters in length. You can imagine if we would somehow split, exfoliate this tube, it's relatively easy to get monolayers or very thin flakes of MOS2. And indeed, when we chemically exfoliated in butyllithium, we got a lot of, actually majority, of the single molecular layers of molybdenum disulfide, which represent the graphene analogy. The flakes are single monolayer, or here at this place there are two monolayers of MOS2. It's interesting that in the water dispersion, these flakes are quite stable. It seems that this spontaneous curvature prevents them against the restacking. And we got a strong blue shift of the excitons, extremely in several EV. So when we calculated, when described theoretically, it came out that majority of these flakes is really one monolayer thick, and because of the quantum confinement, we got this strong blue shift. So now I came finally to the lubricating properties of MOS2 nanotubes. You know that molybdenum disulfide is non-lubricant, and why the tubes would be better lubricant as normal flakes? Because of this cylindrical geometry, because they are always in a right direction. They are not perpendicularly oriented to the counter surfaces. So we expected good lubricating properties. And indeed, when we added 5% of the nanotubes, these coaxial nanotubes, into polyalpha olefin oil, the friction was reduced for 60% and wear for 90%. Here you see the wear traces. This experiment was done only in oil. So these are lines of the polishing, and this is wear trace. So when we added the nanotubes, you still see these lines of the polishing. Only this dark band means that you have molybdenum disulfide there, because it absorbs very well the visible light. We have done experiments that we use these tubes as a lubricant of very much polished surface. This is comparison of the steel coefficient of friction on the steel lubricated with nanotubes, and DLC coatings, diamond-like coatings. Also, diamond light coatings, the friction drops for 50% if, I think 2%, yeah, 2% of molybdenum disulfide is mixed in this polyalpha olefin oil. And now we tested very well polished surface, steel surface, and less smooth surface, and we realized that the final friction is the same. So the final polishing of the steel surface is not necessary anymore if these tubes are used as additive in the lubricant. This is important technological breakthrough. Also, the tubes are compatible with standard extreme pressure and additives based on the zinc. So when we added the alpha olefin oil with molybdenum disulfide nanotubes, the friction dropped again for this miracle value for 50%. So when I report this, sometimes people are so surprised, but all the time we have this 50-60% of the friction drop. Now a few words about nano friction tests. This test was done on mama tubes. Here you see these small babies. So we have done the test on the surface of a single nanotube, on the area where it is empty, and on the area where this nano onion is below. This was done with atomic force microscopy at room temperature, so we follow this bending of the AFM tip. And here you see this is STM image, the high density of states where the nano onion is below the surface. And we realized maybe a trivial or very important fact. So if the tube lied over the step, or it was kinked a little bit over the surface, this means if the tube was not well supported by the substrate, the coefficient of friction was 4 times lower than if the tube lied on the atomically flat surface and it was well supported by this substrate. And we explain this with the dissipation of the energy. So if the energy, the thermal energy caused during the friction process cannot dissipate, the friction is strongly decreased. So this can be a new mechanism, a new generation for the creation, new generation of the lubricants. So here you see this, the results. We also measured the friction on a single nano onion. And now, because I don't have time, you can enjoy the pictures. Only maybe here I will stop for a second or two. So we synthesized also 2 new tungsten oxide platelet compounds with unknown structure, which differ from the well-known tungsten oxides, and this is ongoing work. So we found nice superstructures, as one of the previous speakers explained, and we investigate this further. So instead of the conclusion, I would like to thank my co-workers. I have 2 students, Bojana and Luca Peter. Janez Jelins helped me in the synthesis. At Notre Dame University, they have done transport properties. At our faculty for mechanical engineering, they helped in tribology. And I was in collaboration with Tribology Institute in Vienna. And for the last slide, I would like to show you photo regards from Slovenia. Thank you very much.
Thank you very much. Thank you very much for this nice talk. And now it's open for discussion. I see the first question.
Let's talk indeed. So, we have a common friend, Reshef Tene from Weizmann, sitting in Israel. As you know, I think it's 10 years ago, something like this, he introduced nanotubes of carbon, even at pumps, with oil in Israel. And the problem was coalescence. It means that before introducing the system, nanotubes made coalescence, and from nanos you were something like micro and so on and so on. Are you not afraid about this effect? Have you tried long-term, let's say, effects of your nanotubes in lubricant?
Yes, we have done several hundred hours of the tests, but I can comment also these results from Israel.
Yes.
They mostly focus on nano onions of tungsten disulfide, which show a high tendency of agglomeration.
Conglomerates.
Yeah, they conglomerate. And this is really a difficult problem. But in our case, we don't have nano onions, but we have nanotubes, and they don't show this effect. And also this special structure of mama tubes, this is really excellent because you have these nano onions somehow stored inside these very thin walled tubes. They cannot agglomerate.
So you are convinced to be stable in time?
Yeah, we are convinced that they are stable in time.
Good one.
Thank you.
There is another question.
Sorry, can you grow your nanotubes with stable fixed size of the wall? For example, 3, 10, 20 monolayers along the length, or can you estimate the dispersion of this parameter on the tubes?
Unfortunately, not. But what we succeeded is that we know how to synthesize the nanotubes, which are only 3 micrometers in length and between 100 and 150 nanometers in diameter. So this was the best success. But that we would synthesize with 3, 4, or 5 molecular layers, we don't know how. Sorry.
Do you have a question? No? Okay. Any other questions? If not, then thanks to speaker again. And the other speakers of the session. And now we have lunch break, I think, so.
So, just several announcements. First of all, you are invited to follow me to the next building for the conference photo on the steps outside. Gail, photographer, will do that. After that, lunch, wherever you wish. After 2 o'clock, sessions in sections and in the next building. And at 6:15, I will be waiting for you at the entrance to the main building of the university near the buses with inscriptions conference. And we will go to a very nice concert with our chamber orchestra. So photo, lunch, sections, concert. Enjoy your day.